You wake up. But something is wrong. Terribly wrong. The first thing you notice is the cold seeping into your fingertips. You look down at the mug of coffee on the floor beside your bed, not shattered, but whole. As you watch, a dark, fragrant liquid that was pooled on the hardwood begins to tremble. It gathers itself, defying gravity, leaping from the floorboards in a graceful, impossible arc and pouring itself back into the pristine white ceramic. The warmth doesn't spread into your hands from the mug. It flows out of them, leaving your skin chilled. A faint, jagged line on the mug's surface seals itself, vanishing without a trace. The memory of it shattering isn't a memory at all. It's a premonition. You remember, with perfect clarity, that you're about to knock it off the bedside table in just a few moments. Yesterday is a complete mystery, a fog of unknowing. But tomorrow you remember with the same certainty that you now remember your own name. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This isn't a dream. This isn't a fantasy. This is a world where time's arrow has been flipped. A universe running in reverse. The experience is disorienting, chilling, and it violates every intuition we have about reality. We live our lives on a one-way street. Causes always precede effects. We remember the past, but we can only guess at the future. An egg, once scrambled, will never spontaneously reassemble itself. A fire will reduce a log to ash, but we'll never witness ash gathering itself into a log, sucking smoke and heat from the air. This one-way flow is so fundamental that we rarely stop to question it. It feels as absolute as gravity. But what if I told you that on the most fundamental level, the laws of physics don't seem to care which way time flows? What if the universe, at its core, is a two-way street, but for some reason, we're all trapped in the forward-moving lane? The answer to this profound mystery lies not in some undiscovered law, but in a concept that governs everything from your morning coffee to the ultimate fate of the cosmos. It's a concept often described simply as disorder or chaos, but its true meaning is far more elegant. The secret to why your coffee doesn't unspill, why you can't remember tomorrow's breakfast, and why the universe as we know it even exists, is a single, inescapable idea: entropy. Let's pull back the curtain on time itself and journey from our familiar world deep into the bizarre realm of quantum mechanics and thermodynamics, to understand what time's arrow truly is, and what it would really mean to live in a world where it points the other way. The great deception of physics. To start our journey, we have to confront a deeply unsettling fact. The most fundamental laws of physics, the rules that dictate everything from galaxies to subatomic particles, mostly work just as well forwards in time as they do backwards. Imagine watching a video of the Earth orbiting the Sun. It's a graceful, predictable ellipse, governed by gravity. Now, play that video in reverse. The Earth would simply trace the exact same path, just in the opposite direction. Nothing would look physically wrong. The laws of gravity, described by both Newton and Einstein, don't have a preferred direction for time. You can replace the time variable, t, with t, in the equations, and they still hold true. Or picture two billiard balls colliding. You see the cue ball strike the red ball, transferring its momentum. Now, run that film backwards. The red ball comes in, strikes the stationary cue ball, and stops dead, sending the white ball moving away. It might look like an incredible trick shot, but it doesn't violate any core principles of physics like the conservation of momentum and energy. This time symmetry holds true for electromagnetism and the strong nuclear force, too. It seems that at the microscopic level, the universe has no preference for past or future. But here's the twist. It's not a perfect symmetry. Since the 1960s, we've known about something called CP violation, and thanks to a bedrock principle of physics known as the Kapton theorem, this implies that time symmetry must also be broken. This isn't just theory. In 2012, the Babar collaboration directly observed this time reversal violation in the behavior of certain subatomic particles called B mesons. They found that these particles change from one state to another at a different rate than the reverse process happens. This confirms that the weak nuclear force, one of the four fundamental forces of nature, does indeed have a built-in direction for time. This deepens the paradox. The laws governing almost everything we see, gravity, electromagnetism, the strong force, are time symmetric. Yet, one fundamental force isn't, and on top of that, our macroscopic world has an undeniably strong, irreversible direction. Why do we see buildings crumble into dust, but never see dust spontaneously assemble into a building? It's as if the universe is built on rules that are mostly reversible, yet it only ever plays the game in one direction. The arrow of time isn't written into the code of a single particle. It's an emergent property. It arises not from a command, but from probability. The source of this one-way street is the collective behavior of trillions of particles, all governed by the relentless laws of statistics. The answer, as we'll see, lies in the second law of thermodynamics, a principle the great physicist Arthur Eddington believed held the supreme position among the laws of nature. He once said, "If your theory is found to be against the second law, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." That law is all about one thing: entropy. The universe's organizing principle. So, what is this powerful concept, entropy, that dictates the flow of our entire universe? Simply put, entropy is often described as a measure of disorder. A tidy room has low entropy, a messy room has high entropy. An intact egg is a low entropy state. A scrambled egg is a high entropy state. But this is just a starting point. Entropy isn't just about messiness, it's about probability. The second law of thermodynamics states that in an isolated system like our universe as a whole, total entropy will never decrease. It can only stay the same or, much more likely, increase. This isn't a command that particles must obey. It's a law of overwhelming statistical odds. Let's think about this in terms of microstates and macrostates. A macrostate is the overall appearance of a system. For example, a cup of coffee with cream sitting on top is one macrostate. The coffee and cream fully mixed is another. A microstate is the precise arrangement of every single molecule in that system. Here's the key. For the initial, separated, macrostate, there's a relatively small number of ways to arrange the molecules. This is a low entropy state. But for the mixed, macrostate, the cream and coffee molecules can be arranged in a staggering, almost infinite number of ways. The mixed state corresponds to a vastly larger number of possible microstates. This is a high entropy state. The second law simply says that systems naturally evolve from states with fewer possible arrangements to states with more possible arrangements, because the latter are statistically far more probable. The molecules are constantly jiggling around. It's statistically inevitable they will wander from the rare, ordered arrangement into one of the countless trillions of disordered ones. It's not a force pushing them to mix. It's just that there are colossally more ways to be mixed than to be separate. Expecting the mixed coffee to spontaneously unmix is not technically forbidden by physics. It's just so mind-bogglingly improbable that we'd have to wait longer than the age of the universe to see it. It's like flipping a coin 1,000 times and getting heads every single time. It could happen, but you wouldn't bet on it. This principle is universal. Think of the air in the room you're in. It's spread out evenly, a high entropy state. It's physically possible for all the air molecules to spontaneously rush into one corner, leaving you in a vacuum. But the number of arrangements for that all in one corner. State is so infinitesimally small compared to the spread out state that it will never, ever happen. You are safe from spontaneous suffocation because of the second law of thermodynamics. This relentless, statistical march from order to disorder, from low entropy to high entropy, is the thermodynamic arrow of time. It's why heat always flows from a hot object to a cold one. The past is the state of lower entropy. The future is the state of higher entropy. The flow of time we experience is the universe falling into progressively more probable states. While this is the dominant view, some recent research suggests the relationship between entropy and time's arrow might be even more complex, but for our day-to-day world, it's the law. The mind's one-way mirror. We've established that the universe has a powerful direction painted by the broad strokes of entropy. But how does this cosmic principle translate into our own, personal experience of time? This is the psychological arrow of time. The direction in which we feel time passes and accumulate memories. It turns out these two arrows, the thermodynamic and the psychological, are fundamentally the same. Why can you remember what you had for breakfast yesterday but not what you'll have for breakfast tomorrow? A memory isn't an abstract concept. It's a physical trace in your brain. When you learn something, your neurons fire in a specific pattern, strengthening connections and creating a physical record, a state of relative order in your brain's complex network. But creating this order comes at a cost. Your brain is a bustling, energy-hungry organ. To form a memory, your brain burns glucose and powers electrical signals. This whole metabolic process is inefficient. As your brain creates a structured memory trace, a local decrease in entropy, it releases a significant amount of waste heat into your surroundings. This release of disorganized energy represents a massive increase in the overall entropy of the universe. So, for the tiny bit of order created in your brain that we call a memory, a much larger amount of disorder is created everywhere else. A memory is a record of a past, lower entropy state, created by a process that drives the universe toward a higher entropy future. As physicist Sean Carroll puts it, our ability to remember the past but not the future is ultimately explained by the fact that entropy was lower in the past. This gives us a profound explanation for our subjective experience of time. We remember the past because the past is where the low entropy states are. We cannot remember the future because it's the unknown, high entropy territory into which the universe is expanding. Our feeling of the present moment is an illusion created by this asymmetry. We exist at the boundary between a recorded past and an unwritten future. Our consciousness is constantly turning the uncertainty of the immediate future into the certainty of a recorded memory. This continuous act of creating records, leaving a wake of memories behind us, generates the psychological sensation of time's passage. In a universe at maximum entropy, or heat death, there would be no arrow of time. Everything would be a uniform, tepid soup of particles. Nothing interesting would happen. There could be no memory, because forming a memory is an entropy-increasing process. Without an increase in entropy, there's no distinction between past and future, and therefore, no time as we know it. Life isn't a fight against the second law. It's a consequence of it. The backwards world revisited. Now, armed with our understanding of entropy, let's return to that chilling opening scene. What would a universe with a reversed arrow of time truly be like? It's far more bizarre than just watching a movie in reverse. A universe with decreasing entropy would be one moving from high probability to low probability. Heat would spontaneously flow from cold objects to hot ones. Stars wouldn't radiate energy. They would absorb it, growing hotter and more compact. The universe wouldn't be expanding. It would be contracting, tidying itself up. The most profound consequence would be the reversal of cause and effect. In our world, a cause, knocking over a glass, leads to an effect, the glass shatters. In a backward world, the effect would precede the cause. You would see shards of glass on the floor, which would then leap up and assemble into a whole glass in your hand, followed by the uncausing motion of your hand nudging it off the table. This inversion would shatter our conscious experience. Since memories are records of lower entropy states, in a world of decreasing entropy, our brains would form records of the future, the direction of lower entropy. You would wake up with a perfect memory of every event that was going to happen that day. You'd remember a phone call moments before the phone rang. The future would be a fixed script you were destined to unexperience. The past, however, would be a complete blank. Communication would break down. You'd hear the answer to a question before you asked it. Learning would be an act of forgetting. Life itself, as a biological process that maintains order by expelling disorder, would be impossible. It wouldn't be a fountain of youth. It would be a march into non-existence. While this total reversal seems like pure fantasy, scientists are discovering that time's arrow might not be so absolute. Recent 2025 research from the University of Surrey suggests that at the quantum level, time could theoretically flow both forwards and backwards in certain systems. And in another 2025 breakthrough, researchers used programmable metamaterials to achieve a repeatable, controlled temporal reversal of electromagnetic waves in a lab. This doesn't reverse macroscopic time, but it shows that the line between science fiction and reality is getting blurrier. The cosmic beginning and end. We've followed the arrow of time from a cup of coffee to the wiring of our brains. But this raises the ultimate question. Where did this arrow come from in the first place? If the universe is evolving toward higher entropy, it must have started in a state of incredibly low entropy. Why? This is one of the deepest mysteries in physics, taking us back 14 billion years to the Big Bang. The answer is linked to the past hypothesis, which posits that the universe began in a very special, highly ordered, low-entropy state. This might seem strange. We picture the Big Bang as a chaotic explosion. But in thermodynamic terms, it was the opposite. It was a state of near-perfect uniformity. For a system governed by gravity, a smooth distribution of matter is actually a very low-entropy state. Gravity likes to clump things together. A dispersed cloud of gas has low gravitational entropy. As gravity pulls that gas into stars and galaxies, the entropy increases. The clumpy universe we see today is a higher entropy state than the smooth soup that existed just after the Big Bang. So, the Big Bang was the cosmic wind-up key. It set the universe up in an improbable, low-entropy configuration. The entire 14 billion-year history of cosmic evolution is the universe's slow journey from that special state toward maximum entropy. The arrow of time is cosmological. We perceive it in our daily lives because we live in the aftermath of that event. Why the universe began in this special state is a question that pushes the boundaries of known physics. Some theories suggest it was a fluctuation in a larger multiverse. Others speculate about cyclical universes where the end of one becomes the low-entropy beginning of the next. But for our universe, the fact remains. We started with an arrow, a gift from the Big Bang. This arrow points toward an ultimate future. Trillions of years from now, the last stars will burn out. All matter may be consumed by black holes, which will themselves evaporate over unimaginable timescales. The universe will become a cold, dark, and empty place, a diffuse gas of particles near absolute zero. This is the heat death of the universe, a state of maximum entropy. There will be no energy flow, no change, no complexity. The arrow of time will cease to have meaning, because there will be no more entropy left to increase. Time's journey will be over. We started with an impossible image. Coffee leaping back into its mug. We've discovered that this simple event is tied to the grandest story of all, the story of the universe. Time's arrow isn't a fundamental law that forbids going backward. For the most part, the laws of physics are indifferent. Instead, time's arrow is a statistical truth, born from the collective behavior of countless particles on a journey called entropy. Our universe was born in a state of extraordinary order, a low-entropy configuration set by the Big Bang. The forward march of time is simply the universe evolving from that improbable beginning toward more probable, disordered states. It's why eggs scramble and never unscramble. We've seen that our minds are slaves to this same law. Our ability to remember the past but not the future is a direct consequence of this flow. Memories are ordered traces of a lower entropy past, created by processes that increase the total chaos of the cosmos. Our sense of a moving present is an emergent phenomenon that exists only because entropy is always increasing. To imagine a world where time flows backward is to imagine a universe of inverted causality, where life and consciousness as we know them would be impossible. So, the next time you stir milk into your tea and watch it swirl from order into beautiful, chaotic patterns, take a moment. You're not just witnessing a simple act of mixing. You are seeing the same principle that set the universe in motion 14 billion years ago and that paints the direction of every moment of your life. While a day flowing backward is a mind-bending fantasy, every ordinary moment we experience is a quiet testament to the unstoppable, creative, and forward march of entropy. If this journey through time challenged your perception of reality, let us know what you think in the comments. We love exploring the biggest questions of the cosmos. And now, a question for you. If you could witness one single event happening in reverse, what would it be? Your answer might reveal more about the arrow of time than you think. The one cosmic law that makes life irreversible. Imagine you could rewind your life. Not just the last 5 minutes, but all of it. Imagine your wrinkles smoothing away, your body growing younger, and memories of tomorrow flooding your mind while yesterday becomes a total mystery. Imagine watching buildings unbuild themselves, forests shrink back into seeds, and the great cities of the world dissolve into quiet fields. Sounds like a weird dream, a fantasy. But what if I told you that the only thing stopping this from happening, the one thing keeping our universe on a one-way track from past to future, isn't some mystical force, but a single, fundamental, and absolutely unbreakable law of physics? Now, here's the strange part. The deepest laws of physics don't really seem to care if time runs forwards or backwards. A video of planets orbiting the sun looks perfectly normal in reverse. So why is our world so different? Why are we all living on a one-way street? The answer is hidden in the most mundane events you can think of. It's in the coffee cooling on your desk, an ice cube melting in your glass, and the simple, irreversible act of dropping a cup and watching it shatter into 1,000 pieces. Watch this. A ceramic cup, held in the air. I let go. It falls, hits the ground, and shatters. The pieces scatter. It's a mess. Now, have you ever in your entire life seen the reverse happen? Have you ever seen 1,000 scattered pieces of ceramic suddenly leap off the floor, fly through the air, and perfectly reassemble themselves into a pristine cup, landing gently back in your hand? Of course not. It feels like the most obvious piece of common sense in the world. That just doesn't happen. But why? Behind that simple, irreversible act lies the most profound and powerful law in the cosmos. It's a law that explains why you age, why you remember the past but not the future, and why the universe itself seems to have a one-way ticket from a fiery birth to a cold, dark end. This is the story of entropy. It's the story of the arrow of time. And understanding it means understanding why our existence, our memories, and our world are so fundamentally, beautifully, and tragically irreversible. A universe of possibilities. Our journey starts not out in the cosmos, but with something much simpler. A deck of cards. Picture a brand new deck, fresh from the box. It's in what we call new deck order. Ace of spades, 2, 3, all the way to the king. Then the next suit, and the next. Perfectly ordered. We can call this specific arrangement a state of very low entropy. It's neat, predictable, and special. Now, let's just shuffle it. One shuffle. The order is disturbed. A few cards are out of place. Shuffle it again. And again. With every shuffle, the deck gets more and more jumbled. The suits are mixed, the numbers are all over the place. After a dozen shuffles, the deck is in a random, chaotic state. This is high entropy. So here's the big question. If you just keep shuffling, what are the odds that you'll accidentally shuffle those cards back into perfect, new deck order? The answer isn't zero. It's asterisk technically possible. But the number of possible random arrangements of 52 cards is staggering. It's 52 factorial. That's a number that starts with an 8 and has 67 other digits after it. It's so vast that if every star in our galaxy had a trillion planets, each with a trillion people, and every one of them shuffled a deck a trillion times a second since the Big Bang, we still wouldn't have even scratched the surface of all the possible combinations. There's only one way for the cards to be in perfect new deck order. But there are astronomically huge numbers of ways for them to be a jumbled mess. So when you shuffle, you aren't being pushed towards chaos by some mysterious force. You are simply, by pure statistics, overwhelmingly more likely to land on one of the trillions upon trillions of disordered states than on that single, unique, ordered one. It's not a law of force, it's a law of probability. And that's the key idea. Entropy isn't really about messiness. It's about the sheer number of ways things can be. Think of a sandcastle. There's a limited number of ways you can arrange sand grains to make a perfect castle. But how many ways can you arrange them to just be a pile of sand? A practically infinite number. The wind and waves don't have a personal vendetta against sandcastles. They just move sand grains around randomly, and it's just overwhelmingly more probable that this will result in a pile of sand than a castle. Let's look at the classic physics example. Imagine a box with a divider in the middle. On the left, we have a gas billions of particles bouncing around. The right side is a perfect vacuum. This state, with all the gas on one side, is organized. It's low entropy. Now, we remove the divider. What happens? The gas particles, in their random motion, spread out. In a flash, they distribute themselves more or less evenly throughout the whole box. They've gone from a low entropy state, all on one side, to a high entropy state, spread out. And just like the cards, will you ever see all those particles spontaneously decide to move back to the left side, leaving a vacuum on the right? Again, not forbidden by the laws of motion for any single particle. But for all of them to coordinate their random movements to end up on one side is as statistically impossible as shuffling a deck back into perfect order. The odds are so small, we can confidently say it will never, ever happen. We see this everywhere. A drop of ink in water disperses until the water is uniformly colored. It never regathers. Perfume sprayed in a corner spreads out. It doesn't collect itself back into the corner. These are all things moving from a state with fewer possible arrangements, ink in a tiny drop, to a state with vastly more possible arrangements, ink spread through the water. This relentless, statistically driven march from the unlikely to the likely, from order to disorder, is the engine of our universe. And it has a name. The second law of thermodynamics. The law. Forging an arrow. The second law of thermodynamics is one of the most ironclad laws in science. Simply put, it says that in any isolated system, one that doesn't exchange energy with its surroundings, like our universe as a whole, the total entropy, the total amount of this statistical disorder, will always increase or stay the same. It can never decrease. This idea didn't come from staring at the stars. It came from something much more practical: steam engines. In the early 19th century, the French physicist Sadi Carnot was obsessed with engine efficiency. He realized that to get work done to push a piston or turn a wheel, you need a temperature difference. You need a hot source, like burning coal, and a cold sink, like the air. Work happened as heat flowed from hot to cold. This flow of energy from concentrated to dispersed is what drives all engines, including the engine of the universe itself. But it was the Austrian physicist Ludwig Boltzmann who, in the 1870s, connected this industrial observation to the world of atoms. He proposed that the second law wasn't a fundamental force like gravity, but a statistical reality born from the behavior of countless particles. It was Boltzmann who gave us the profound equation now famously engraved on his tombstone: S equals K log W. Let's break it down. S is entropy. K is just a number, the Boltzmann constant. And W stands for the number of ways, the number of microscopic arrangements that look like the single macroscopic state we see. And here's where we need to clear up a common misconception. Entropy is often just called disorder or messiness. But a more accurate, more powerful way to think about it is as the dispersal of energy. Let's go back to our shattered cup. The intact cup is low entropy. Why? All its molecules are locked in a very specific, rigid structure. There are relatively few ways you can arrange those molecules and still have an intact cup. But when it shatters, the pieces can be scattered on the floor in an almost infinite number of positions, and we'd still call it a shattered cup. The W, the number of possible arrangements, has skyrocketed. Entropy has increased. An egg is a low-entropy object. Its proteins and fats are neatly organized. When you scramble it, you break those structures down and mix everything up. There are vastly more ways for those molecules to be mixed up than to be neatly separated. So, entropy increases. You can break an egg, but you can't unscramble it. Not because of some no unscrambling rule, but because the scrambled state is so statistically probable and the unscrambled state is so improbable that the universe, in its random shuffling, will never find its way back. This is the heart of the second law. The universe isn't trying to become messy. It's just exploring possibilities, and there are overwhelmingly more ways to be high entropy than low entropy. Heat flows from your hot coffee to the cold room because there are more ways for the energy to be shared between the cup and the room than to be stuck in the cup. The energy disperses, entropy increases, and your coffee gets cold. This relentless, one-way increase of entropy is the most fundamental asymmetry in nature. The basic laws of physics, Newton's laws, electromagnetism, even quantum mechanics, are time-symmetric. They work just as well forwards as they do backwards. But the second law is different. It has a direction. It tells us that things change in one direction only, towards higher entropy. This law, born from steam engines and statistics, is what forges the arrow of time itself. It's a mind-bending thought. The feeling you have of time moving forward, the very line between past and future, is a consequence of cosmic probability. Getting a real handle on these deep concepts sometimes requires rewiring your intuition. If this journey into the nature of reality is sparking your curiosity, you might love Brilliant.org. Brilliant is an interactive learning platform that makes complex subjects in math and science genuinely accessible and fun. Instead of just watching, you actually solve hands-on problems that build your intuition step by step. Their course on classical mechanics, for example, can give you a new appreciation for those time-symmetric laws Boltzmann was working with. And their courses on thermodynamics will let you explore the very concepts of entropy and energy we're talking about right now, but in a much more interactive way. You really do learn by doing, which is the best way to grasp these abstract ideas. To get started for free, you can go to Brilliant.org. Unlocking the universe. The first 200 people to use that link will also get 20% off an annual premium subscription. By using it, you're not just investing in your own knowledge. You're also directly supporting this channel, allowing me to make more videos just like this one. So, check out Brilliant, and let's get back to the beginning of time. The arrow of time. Why we remember yesterday. So, the universe tends towards higher entropy. But what does that really have to do with our personal experience of time? Why does this statistical law make us feel like we're moving in a straight line from a fixed past to an open future? The connection is profound, and it gets to one of the most intimate parts of our consciousness: memory. Think about it. Why do you remember yesterday, but not tomorrow? It sounds like a silly question, but it's one of the deepest puzzles in physics. The answer, according to physicists like Sean Carroll, is that creating any kind of record, including forming a memory in your brain, is fundamentally an entropy-increasing process. A memory is an ordered arrangement of neurons. Creating that order takes work. When your brain forms a memory of, say, that cup shattering, it arranges neurons into a specific pattern that encodes the event. But this process isn't a free lunch. To do it, your brain has to burn energy from the food you ate, and that process pumps out a ton of waste heat into your surroundings. This release of heat disperses energy and increases the asterisk total entropy of the universe far more than the tiny bit of order created by the memory itself. So, you can form a memory of an event only because the overall process increases the total entropy of the universe. This is what we call the psychological arrow of time, the direction in which we build memories. And it points in the exact same direction as the thermodynamic arrow of time, the direction of increasing entropy. We remember the past because the past was a lower entropy state than the present. The universe is a story being written in the language of increasing entropy. We can read the chapters already written, the past, because they led to where we are now. But we can't read the chapters that are yet to come, the future, because they haven't happened yet. The future is just an open realm of high entropy possibilities, a statistical fog. The past is the single, low entropy path that got us here. This is why we see cause and effect. We see the cup fall, then it shatters. Cause, then effect. We never see the shatter cause the cup to reassemble and leap into the air. That's because the initial state, the intact cup, is a simple, low entropy state. The laws of physics evolve it forward into one of the countless possible high entropy states, a shattered mess. To go backwards, you'd need an impossibly fine-tuned, high-entropy state, all the pieces with perfectly coordinated velocities, to evolve into a single low-entropy one. Probability just says no. The arrow of time, then, isn't a property of time itself. It's an emergent property of the stuff in the universe. It's a direct consequence of the fact that entropy is always increasing. Time feels like it flows forward because that's the direction of greater probability, of energy dispersal, of the universe moving from special, ordered states to generic, disordered ones. But this raises an even bigger, more profound question. If the universe is always getting more disordered, then that must mean that in the past, entropy was lower. And yesterday, it was lower still. If you follow that logic all the way back, as far as you can possibly go, you must arrive at a moment in time when the universe was in a state of the most unbelievable, absolute, astonishingly low entropy imaginable. If entropy is the arrow of time, where did we get the arrow? To answer that, we have to go back to the beginning of everything. The cosmic origin, the unlikely beginning. For the arrow of time to even exist, our universe needed a starting point. And not just any starting point, it needed a very, very special one. It needed to begin in a state of extraordinarily low entropy. Cosmologists call this the past hypothesis, and it's the ultimate anchor for our arrow of time. Without it, the universe would just be a timeless, boring soup at maximum entropy, where nothing ever happens, a state known as heat death. So, where did all this order come from? The answer lies at the very beginning, 8 billion years ago, in the Big Bang. Now, when we think Big Bang, we imagine a chaotic explosion. But in a thermodynamic sense, the very early universe was the opposite of chaos. It was a state of sublime, almost perfect order. It was a hot, dense, incredibly smooth, and uniform soup of particles and energy. I know what you're thinking. How can a hot, uniform soup be low entropy? Isn't a smooth mixture a high entropy state, like the ink mixed in water? This is where we have to introduce the most important player in the cosmic game: gravity. For a gas in a box, being spread out and uniform is indeed high entropy. But for a system governed by gravity, the opposite is true. Gravity wants to pull things together. So, a smooth, uniform distribution of matter is actually an unstable and therefore low entropy state. Gravity wants to form clumps. It wants to pull gas into stars, stars into galaxies, and galaxies into clusters. From a gravitational perspective, a clumpy universe is a high entropy universe. The early universe, being almost perfectly smooth, was in a state of incredibly low gravitational entropy. It was like a perfectly balanced pencil standing on its tip, a state of immense potential, ready to fall into a more disordered, clumpy state. That initial smoothness is the foundational miracle that makes everything else possible. It's the original, perfectly ordered deck of cards from which the entire history of the cosmos has been shuffled. Over the last 8 billion years, gravity has been doing its thing. It has pulled matter together, forming the magnificent, complex structures we see today. And every step of this process, gas collapsing into a star burning fuel, a star exploding, is an entropy increasing process. The universe has been moving from that initial, smooth, low entropy state towards a clumpier, higher entropy one. The formation of galaxies isn't a sign of order, it's a sign that the second law is at work on a cosmic scale. And the process isn't over. The arrow of time, launched at the Big Bang, is still flying. Stars will burn out. Galaxies will drift apart. Even black holes, which are states of enormous entropy, are thought to eventually evaporate over unimaginable timescales through Hawking radiation. Follow this trend to its ultimate conclusion, and you arrive at the predicted fate of our universe: heat death. A state of maximum entropy. The universe would be a vast, cold, dark, and perfectly uniform void. All temperature differences would have evened out, so no energy could flow and no work could be done. No stars, no life. All processes would just stop. The arrow of time would have nowhere left to point. Time, as we know it, would effectively end, because in a state of perfect equilibrium, nothing ever changes. So the story of our universe is a journey between two states. It begins with the profound mystery of the Big Bang's low entropy, a state of perfect order. It ends with the cold, timeless equilibrium of heat death, a state of perfect disorder. And everything in between, every star that shines, every planet that forms, every life that emerges, is part of that grand, irreversible unfolding. The shattering of a cup on your floor is a tiny echo of this very process, carrying forward the drive toward higher entropy that the universe began with. Life's brief, ordered rebellion. So, we've gone from a shattered cup to the very beginning and the predicted end of time. We've seen that the one-way street of life is governed by a simple law of probability. The second law of thermodynamics, which says the total entropy of the universe must always increase. This law forges the arrow of time, driving the cosmos from a special, ordered beginning towards a final, disordered state of heat death. It's easy to hear this and see it as a destructive force, a cosmic sentence of decay. Entropy is what makes things break, wear out, and fade. It's why our bodies age, our creations crumble, and even the stars will one day die. It can paint a pretty bleak picture of a universe inevitably sliding into a cold, empty abyss. But there's another way to look at it. Entropy isn't just the law of decay. It is also the law of change. The relentless increase of entropy is what makes things happen. The flow of energy from a low entropy source to a high entropy sink is what powers everything. The sun is a magnificent ball of low entropy energy. The light that travels from it to the earth is highly ordered. And that flow of energy is what allows plants to grow, what drives our weather, and what makes our world a dynamic, vibrant place. And that leads us to the most remarkable phenomenon in the known universe: life. Life seems like a paradox. It is a pocket of exquisite order in a universe that's constantly running towards disorder. Just look at the complexity of a single cell, its intricate molecular machinery, its DNA packed with information. It's a masterpiece of low entropy. Does this mean life violates the second law? Not at all. A living thing, like you, maintains its incredible internal order by importing low entropy energy from its environment, food, sunlight, and exporting high entropy waste, heat, carbon dioxide. The very process of living, of thinking, moving, growing massively increases the entropy of the universe around you, far more than it decreases the entropy inside you. Life doesn't defy the second law. It exploits it. Life exists not in spite of entropy, but because of it. It's a beautiful, temporary, and localized rebellion against the universal tide of disorder. Think of a surfer on a wave. The wave, the flow of entropy, is an unstoppable force heading for shore. But for a brief moment, the surfer can harness the energy of that wave to create something of incredible, dynamic order. So, the next time you see a shattered cup, don't just see it as an act of destruction. See it as a symbol of the profound law that gives our universe a history and a future. That irreversible act is a reminder that we live in a dynamic, evolving cosmos. It's a reminder of the same law that allows the sun to shine, that allows plants to grow, and that allows us, for a brief and precious moment, to exist as islands of complex order, experiencing the universe and wondering about its mysteries. The arrow of time makes life irreversible. We can't go back. But it's also what makes a story possible. And our existence, powered by the relentless march of entropy, is the most extraordinary story of all. Physics says time can run backwards, so why doesn't it? Let your mind wander for a moment. Let the noise of the day just fade into the background. We're about to take a journey, not through space, but through time itself. We're going to explore a universe where everything we know happens in reverse. Where shattered glass puts itself back together, and smoke funnels back into a flame. This isn't just a daydream. It's a world that, according to the deepest rules of physics we know, should be entirely possible. First, we'll uncover a simple, yet mind-bending truth. The fundamental laws of physics are time-symmetric. They honestly don't care about the past or the future. Then, with that unsettling idea in our heads, we'll face the biggest mystery of all. If the rules let us travel backward, why does our reality, our lives, every single moment stubbornly move only forward? What is this invisible current pulling us all in one direction? The laws of physics don't care if time flows forward or backward. Run them in reverse, and they work just fine. So, if the universe allows for time to be a two-way street, why are we all stuck on a one-way trip to tomorrow? The shocking truth of symmetry. At the very heart of the cosmos, there's a set of rules. We call them the laws of physics. They're the silent conductors of this grand cosmic orchestra, and they dictate everything from the slow dance of galaxies to the frantic jitter of a single atom. We think of these laws as strict, but in one key way, they're surprisingly permissive. At their most basic level, most of them have no arrow of time. They are perfectly happy working forward or backward. This is called time reversal symmetry, or T-symmetry. Let's start with something familiar. The world of classical mechanics, first mapped out by Isaac Newton. Picture a game of pool in a perfect, frictionless, airless room. A cue ball hits a red ball. We see the impact, the red ball zips into a corner pocket, and the cue ball stops. Newton's laws, like F equals ma, can describe every tiny detail of this with stunning precision. Now, imagine we recorded that shot and play it in reverse. The red ball flies out of the pocket, glides across the table, and hits the cue ball. The cue ball absorbs the energy and zooms back to where it started. It looks weird, maybe even staged, but does it break any of Newton's laws? Not at all. The math that describes the forward collision works perfectly for the backward one. If you just flip the sign on the final velocities, the laws of physics will happily rewind the past. The math doesn't have a preference. The film playing forward and the film playing backward are both equally valid physical realities. This symmetry isn't just for billiard balls. It's true for the majestic dance of planets and stars. An orbit a planet traces moving forward in time is the exact same path it would trace if time were reversed. The equations for gravity don't have a past or future built into them. But maybe that's just old-school physics. Surely our modern ideas have found time's direction hidden somewhere in the laws? Let's go deeper, into the world of electricity and magnetism. In the 19th century, James Clerk Maxwell gave us equations that unified these forces and described light itself. These equations show how electric and magnetic fields create each other, rippling through space-time as an electromagnetic wave. That's light. It's radio waves. It's the warmth you feel from the sun. Now, let's hit rewind. Imagine a light wave spreading out from a light bulb. If you reverse time, Maxwell's equations still work perfectly. The wave would just travel backward, converging exactly back to its source. The physics doesn't break. Just like with Newton, the basic rules of electromagnetism don't know the difference between yesterday and tomorrow. So, the classical world is time-symmetric. But what about the really fundamental level, the strange, probabilistic world of quantum mechanics? This is the realm of the smallest things. Here, reality is described by wave functions, which are basically clouds of probability. The master equation that dictates how these wave functions change over time is the Schrödinger equation. And in its purest form, for a totally isolated system, it's also time-symmetric. If you have a particle's wave function, you can use the Schrödinger equation to see how it will evolve. But you can just as easily run the equation backward to see what it looked like in the past. The math works both ways. The process of one particle bouncing off another can be played in reverse, and it's still a perfectly valid quantum event. This is the shocking truth, the central mystery. From the clockwork of the planets, to a flickering light bulb, to the ghostly dance of an electron, the fundamental laws of physics appear to be time-symmetric. They describe a universe that should be just as happy to run backward as it does forward. A video of these tiny, isolated events would be impossible to judge if it's playing forward or backward. It's like finding the blueprint for a car and discovering the engine is designed to run just as well in reverse. The unyielding reality of the arrow. But that's not the world we live in, is it? Our journey now takes a sharp turn from the clean, theoretical world of equations to the messy, undeniable reality of our own lives. We've seen that the microscopic laws of physics are like a two-way street. Yet, our everyday experience feels like a one-way highway with no off-ramps. Think about a simple act. You drop a ceramic mug. It hits the floor and shatters into 100 pieces. An everyday, irreversible event. Now, can you imagine the reverse? Would we ever expect to see those scattered shards suddenly jump together, the cracks seal themselves, and the mug leap back into your hand, perfectly whole? It's not just unlikely, it feels absurd. The laws might allow it, but reality forbids it. Or take another example. You crack an egg into a hot pan. The clear part turns white, the yolk cooks, it becomes a fried egg. We can describe the chemistry of it all. But can you imagine the reverse? A fried egg in a pan spontaneously cooling, turning clear and liquid again, and flowing back into a perfectly sealed, uncracked shell. The thought is ridiculous. We remember the past, the whole egg, but we'll never see it reassemble itself. This one-way flow of events is what physicists call the arrow of time. It's the deep, constant difference between the past and the future that we experience all the time. It's why cream mixes into coffee but never unmixes. It's why smoke pours from a fire but never gathers itself from the air to rebuild a log. These are all irreversible processes, events that happen in one direction only. This arrow isn't just out there, it's wired into our consciousness. We have memories of the past. You remember what you ate for breakfast, what happened yesterday, the feeling of a childhood vacation. But can you remember tomorrow? Can you recall next week's events with the same clarity you recall last week's? Of course not. We can guess, we can predict, but we can't remember the future. This psychological arrow of time is one of the most basic parts of being human. And here we are, at the great paradox. On one hand, the fundamental laws of nature, classical, electromagnetic, quantum, are mostly indifferent to the direction of time. On the other hand, we have our universal experience of a world that moves relentlessly forward. The microscopic world plays by rules that allow time to be a calm, two-way river. But the macroscopic world we live in is a raging, one-way waterfall. If the basic building blocks of the universe don't have a preferred direction, where does this powerful, all-encompassing arrow come from? To solve this mystery, we have to turn from the laws themselves to a suspect that was hiding in plain sight: the science of steam engines. The prime suspect in the cosmic crime scene. To solve the mystery of time's arrow, we have to look at one of the most powerful laws in all of science: the second law of thermodynamics. It was born from the very practical 19th century study of steam engines, but it's grown to explain everything from why stars die to the direction of time itself. The second law introduces a concept called entropy, which is often described as a measure of disorder or randomness. The law states that in an isolated system, entropy can only stay the same or increase. It never, ever goes down. This relentless increase in entropy is our prime suspect for the arrow of time. To get why, we need to think about entropy as more than just disorder. More precisely, it's a measure of the number of ways you can arrange the microscopic parts of a system to get the same macroscopic state. Think about your bedroom. A low entropy state is very specific and ordered. The books are perfectly aligned, the clothes are folded, the bed is made. There are very few ways to arrange things for the room to be perfectly tidy. Now, what about a high entropy state? That's a messy room. The books are scattered, the clothes are on the floor. How many ways can you arrange the items for the room to be messy? A practically infinite number. A sock on the chair or on the floor, still messy. A book here or there, still messy. There are vastly, colossally more ways for a system to be disordered than for it to be ordered. This is the statistical heart of the second law. Systems don't get messier because of some active force pushing them toward chaos. They get messier simply because being messy is astronomically more probable. When your mug shatters, it goes from a single, highly ordered state, a whole mug, to one of a near infinite number of disordered states, broken pieces. The odds of all the random vibrations of atoms spontaneously pushing those shards back into the one single, whole mug configuration are so small, it would never happen in the lifetime of the universe. It's not that the laws of physics forbid it, it's just statistically impossible. The same is true for the egg. There's one state called uncracked egg, and trillions upon trillions of states called scrambled egg. The system just moves into the most probable state available, which is always one of higher entropy. The forward arrow of time, from this point of view, is simply the universe moving from less probable states to more probable ones. This explains why mugs break, but it raises an even deeper question. If the universe is always getting more disordered, it must mean that in the past, it was more ordered. And if you go all the way back to the beginning, it must have started in a state of incredibly low entropy, a state of profound and perfect order. This is exactly what our cosmological observations suggest. The universe began around 13.8 billion years ago in what we call the Big Bang. At that moment, all matter and energy were compressed into an incredibly hot, dense, and uniform state. Now, hot, dense, and uniform might sound chaotic, but for a system ruled by gravity, a smooth and uniform state is actually a state of incredibly low entropy. A high entropy state for a gravitational system is clumpy and messy. Think of matter collapsed into countless black holes. So, the Big Bang was the ultimate picture of cosmic order. It was the universe like a perfectly wound-up clock. The arrow of time we experience is the universe unwinding from that special starting point. But is that the whole story? While entropy is the main character, there are other, more subtle clues. One of the cornerstones of particle physics is called Kaplan symmetry. It says the laws of physics stay the same if you do three things at once. Swap a particle for its antiparticle. Charge, c, take its mirror image, parity, p, and run it backward in time, t. For a long time, physicists thought c, p, and t were all perfect symmetries on their own. Then, experiments in 1957 and 1964 showed that the weak nuclear force which is involved in radioactive decay violates both p and the combined CP symmetry. This was a huge discovery. According to the Kaplan theorem, if CP symmetry is violated, then to keep the overall Kaplan symmetry intact, T symmetry must also be violated. This means there is a fundamental force that actually does distinguish between past and future. The effect is tiny and doesn't explain why eggs don't unscramble, but it's a profound crack in the symmetric facade of nature's laws. There's one more piece to the puzzle: quantum decoherence. As we said, the Schrödinger equation is time-symmetric for a perfectly isolated quantum system. But in the real world, no system is ever truly isolated. An atom is constantly bumping into air molecules, photons, and background radiation. This constant interaction entangles the system with its environment, and information about its delicate quantum state leaks out. This process is called decoherence. It's what washes out the quantum weirdness and makes things behave in a classical, predictable way. And crucially, decoherence is effectively an irreversible process. Reversing it would mean tracking and reversing the state of every single particle the system ever interacted with, an impossible task. This helps explain how the arrow of time emerges so strongly from the quantum realm. The unwritten beginning. So, where has our journey left us? We started with the startling idea that the fundamental laws of nature are largely time-symmetric, describing a universe that should be able to run forward or backward. Yet, we're faced every day with the one-way flow of time. We saw that this arrow of time is real, and the main reason for it is the second law of thermodynamics. The universe moves from order to disorder, from low entropy to high entropy, because disorder is just vastly more probable. This thermodynamic arrow, however, only works because the universe started in a very special condition, a state of incredibly low entropy. The Big Bang wasn't a messy explosion, but a moment of profound order. The forward march of time is simply the story of that initial order slowly and inevitably unwinding toward a messier future. We also found small cracks in time's perfect symmetry, from a tiny violation in the weak nuclear force to the irreversible process of quantum decoherence. The great mystery has now changed. The question is no longer, why does time only move forward? The evidence points to a clear answer. It moves forward because it started from a highly ordered beginning. The real mystery, the one at the very edge of what we know, is why. Why did the universe begin in such a special, improbable, low entropy state in the first place? Of all the ways the universe could have started, why was ours born with a script that seems written to be read in only one direction? The laws of physics may allow for a world of unscrambling eggs and reforming ashes. But we seem to live in a universe whose first page was written with such perfect order that the story can only unfold, moment by moment, toward the inevitable, high-entropy chaos of its final chapter. The ultimate secret of time lies not in the rules of its telling, but in its unwritten beginning. If this journey through time has sparked your curiosity, consider subscribing and joining us for more explorations into the deepest mysteries of the cosmos. We'd love to hear your thoughts in the comments. What aspect of time do you find most fascinating? Thank you for letting your mind wander with us. The universe is playing in reverse and no one noticed. This is impossible in our universe. A glass of water gets knocked off a table. It shatters, and the water pools into a chaotic, spreading mess. It's a one-way street, something you can't undo. But here's the strange part. The laws of physics, the fundamental rules that run everything, don't actually forbid the opposite from happening. There's nothing in the rulebook that says the shards can't rattle, lift, and spin through the air, clicking back together into a perfect glass that then floats back onto the table, as the puddle of water slithers up its side and pours itself neatly back inside. You live your life watching a movie that only plays forward. Smoke from a blown-out candle thins into the air, a little story of decay. But what if the projector started at the end? What if, somewhere out there, the film is running backward? What if smoke is a sign of a coming fire, a gray mist that gathers from nothing, funnels into a vortex, and dives back into a wick, creating a flame from thin air? What if the universe is playing in reverse, and we just haven't noticed? This isn't just a fantasy. It's a thought experiment that's hauntingly permitted by the very physics we trust. It forces us to ask a question science is brave enough to whisper. Is our reality the only one? The unyielding arrow. We all feel it, don't we? A constant, relentless push from one moment to the next. The past is a landscape of memories, fixed and unchanging. The future is a fog of possibilities we can't yet see. We call this the arrow of time. The phrase was coined by British astrophysicist Arthur Eddington back in 1927, who realized time has this one-way direction that space just doesn't. You can move left or right, up or down, but you can only ever move forward in time. And this isn't just in our heads. It's woven into everything. Crack an egg into a pan, and you watch it go from an ordered little sphere to a sizzling, messy blob. No matter how long you wait, that fried egg won't reassemble itself into the shell. Pour milk into your coffee, and you see elegant white swirls blossom and then fade into a uniform brown. The milk is never getting back out of that coffee. These aren't just kitchen observations. They're demonstrations of one of the most powerful laws in physics, the second law of thermodynamics. Basically, the second law states that in a closed-off system, things tend to get messier. They move from order to disorder. Physicists call this disorder entropy. And according to this law, the total entropy of the universe can only ever increase. It's the ultimate one-way street. Think of a sandcastle. It's a highly ordered structure of low entropy. But the wind, the waves, the feet of other beachgoers, they all work on it. Grain by grain, it crumbles into a shapeless mound, just another part of the beach. It's moved to a state of high entropy. This steady climb of entropy is what gives time its direction. It's why things break down, why buildings crumble, and why we age. Our bodies are incredibly ordered systems, but keeping that order takes a ton of energy. Over time, the processes that keep us going get less efficient, and we give in to entropy's march. Even memory is tied to this arrow. We remember the past, not the future, because the past is where things happened that caused our memories. It's a chain of cause and effect, and that chain only runs one way. We see the glass fall, then we hear it smash. The cause always comes before the effect. This forward march feels so basic that questioning it sounds absurd. It's the difference between a video playing normally and one in reverse. One looks real. The other looks like a cheap party trick. We just know that smoke doesn't pour back into fires. But what if that intuition, built on a lifetime of watching our little corner of the cosmos, is blinding us to a much deeper, stranger reality? What if the laws writing the story of our universe have a hidden clause that lets the whole story be told backward? The glitch in the code. But here's the glitch. While our big picture world of eggs and sandcastles is ruled by the iron fist of entropy, the microscopic world of fundamental physics tells a totally different story. Down at the most basic level, the laws of physics are pretty much time-symmetric. This means the equations describing how particles interact work just as well whether you run the clock forward or backward. Imagine a video of two billiard balls colliding. One hits the other, they fly off. It all follows Newton's laws. Now, if you play that video in reverse, it still looks perfectly normal. You just see two balls coming together, colliding, and moving off. Nothing about the laws of motion is broken. The same is true for a planet orbiting a star. Forward or backward, the path is the same. Gravity doesn't care which way time is flowing. This creates a huge paradox. If the fundamental rules are reversible, why is our world so stubbornly irreversible? The answer is all about statistics. It's not that it's physically impossible for a shattered glass to reassemble itself. It's just so mind-bogglingly improbable that it might as well be. There's only one way for the glass to be in a single piece. But there are trillions upon trillions of ways for it to be in shattered pieces. A system just naturally drifts toward the state with the most possible arrangements, the state of highest entropy. It's less a law of force and more a law of averages. And this is where our thought experiment really takes off. Our universe seems to have started in a very special, highly ordered, low-entropy state at the Big Bang. Since then, it's been expanding and getting more disordered, giving us our arrow of time. But what if that was just one of two paths? What if the symmetric laws of physics allowed for a second universe to spring from that same point, but on a journey of decreasing entropy? This idea gets even wilder when you bring in one of the most fundamental rules in nature: CPT symmetry. CPT stands for charge, parity, and time. The theorem says that if you take any physical system, flip the charge of every particle, C, view it in a mirror, P, and run time backward, T, this new system will follow the exact same laws of physics. This isn't some fringe theory. It's a cornerstone of modern physics, and we have never, ever seen it violated. The implication is staggering. It means a universe that's a mirror image of our own, where matter is antimatter, left is right, and time runs backward from our perspective is completely allowed by the laws of physics. Our universe might only be half of a perfectly symmetrical equation. So the question becomes, what would that other half, that looking glass universe, actually be like? It's time to step through the mirror. Welcome to the looking glass world. So, what would this looking glass world actually look like? Forget your intuition. We're entering a reality that cleans itself up. Picture a great city. But here, the sounds of construction are the sounds of rubble rising. A pile of shattered bricks on a vacant lot begins to stir. Dust and debris lift from the ground, swirling into a cyclone of recreation. Bricks fly through the air, slotting themselves into walls with impossible accuracy. Steel beams untwist and merge into a skeletal frame. In just a few hours, a ruin becomes a gleaming skyscraper. The city doesn't grow, it heals. Out in nature, the rhythms of life are inverted. A forest floor is blanketed in brown, brittle leaves. But as we watch, the leaves stir and lift from the ground like a flock of birds. They find their way back to bare branches, reattaching seamlessly. Their color floods back in, from brown to red and gold, and finally to a lush, summer green. The forest isn't getting ready for winter, it's retreating from it. Nearby, a river flows not to the sea, but from it. Saltwater rushes inland, getting purer as it climbs mountains, separating into fresh streams that are finally absorbed by the earth. Rain rises from the wet ground, forming into heavy clouds that then thin out into a clear blue sky. And a forest fire? It's an awesome sight. We start in a blackened, desolate landscape of ash. Suddenly, the soot in the air gathers, plastering itself back onto the charred trees. The blackness recedes, revealing healthy bark. Flames flicker into existence, not eating the wood, but shrinking, pulling their heat and light back into themselves. A roaring inferno calms to a gentle fire, then a single spark, which is finally yanked back into a branch as a bolt of lightning retracts from the ground and vanishes into a dispersing cloud. Now, let's zoom out. Far out. We see not an expanding universe, but a contracting one. The light from distant galaxies isn't redshifted, but blue-shifted, as everything rushes back toward a single point. Stars aren't exploding, they're imploding. Vast, cold clouds of gas and dust, the leftovers of a star's death, are rushing inward. They compress and heat up, creating a brilliant flash of light as supernova in reverse that ends with the reformation of a massive star. That star then continues to shrink, its light dimming as it gets younger. The cosmic microwave background, the faint afterglow of our Big Bang, is here a cosmic foreground. A wall of radiation converging from all directions, headed for an infinitely dense point in their future. In this universe, the end isn't a cold, dark void. It's a fantastically bright and energetic beginning. If this trip through a backward reality is bending your mind, go ahead and hit that like button. It lets us know you want more deep dives that challenge everything we think we know. The biggest, most disorienting question is still to come. What would it actually be like to live there? To experience this inverted world firsthand? Share your initial thoughts in the comments below, before we jump into the deepest part of this rabbit hole. The inverted mind. We've seen what this reversed world looks like. But what would it feel like? What about consciousness, memory, the act of living? The answer here is perhaps the most profound part of this whole idea. For someone living in this backward universe, everything would likely feel completely, utterly normal. Their arrow of time would point toward their future, which just happens to be our past. To get this, think about how our own minds work. Our sense of time moving forward is tied to entropy. We remember the past because the past holds the causes for our present state. Memories are physical records in our brains, an increase in our own local order, paid for by a much bigger increase in the universe's disorder. They are the result of things that have already happened. In a universe of decreasing entropy, this chain of cause and effect would presumably be flipped. An intelligent being there might not remember what we call the past, they would remember their future. Imagine waking up with a full memory of the day ahead. You remember the taste of the dinner you're going to eat, a conversation you'll have later. The day ahead is known. But yesterday? The day that's a memory for us? For them, it would be a total mystery. An unknown territory they are always moving away from. The idea of free will would be turned on its head. For us, free will is about choosing our future. For them, the future is already remembered. Their sense of choice would be directed backward. A decision wouldn't be about causing something to happen, but about discovering the reason for something that already did. When you undrink a glass of juice, you aren't choosing your future. You're fulfilling the cause for the effect you already know is there. An empty glass on the table. You're creating a past you can't see. Daily life would be a masterpiece of reverse logic. People would go to a restaurant and sit before a mess of dirty plates. They would then uneat their meal, with food jumping onto their forks and returning to the plate, leaving them feeling hungrier and hungrier. Conversations would start with goodbye and end with hello. You'd know the answer to a question long before it was asked. Most fundamentally, life and death would be inverted. A person's existence might begin as they are pulled from the ground, an old, frail being. They would live their life growing younger, stronger, and smaller. A lifetime of wisdom would fade, replaced by youthful ignorance. Wrinkles would vanish, knowledge would be forgotten. Their journey would end as they shrink into a helpless infant, to be finally unborn, back into their mother, vanishing from the world. It's a life not of becoming, but of unbecoming. A journey from the grave to the womb. And to them, this would seem like the only natural way to live. The two-faced universe. This all may sound like wild science fiction, but some adventurous physicists have built models where this dual reality is not just possible, but required. One of the most elegant is the Janus point theory, from physicist Julian Barbour and his colleagues. Named after the two-faced Roman god who looks to both the past and future, their theory suggests the Big Bang wasn't the absolute beginning. Instead, it was a central point of minimum messiness, the Janus point, from which two universes expanded in opposite directions of time. One of those universes is ours, where entropy increases. The other is its twin, a mirror universe that, to us, looks like it's moving backward in time. But for anyone living there, time would feel perfectly normal. It's our universe that would look like a movie in reverse. In this model, gravity itself naturally creates this moment of minimum complexity, forcing the universe to expand in two opposite, structure-forming directions. Time's arrow isn't some random starting condition. It's a consequence of gravity. What's powerful about this idea is that it opens up fascinating new ways to think about some of cosmology's biggest puzzles. Take dark matter. This invisible substance makes up about 85% of the matter in the universe, and we only know it's there because of its gravity. While Barbour's model doesn't focus on it, some physicists have speculated that CPT-symmetric models like this could provide a home for particles that might explain dark matter's effects. The Janus point model also offers an alternative to cosmic inflation, the idea that the universe went through a period of hyper-expansion right at the beginning. Inflation was proposed to explain why our universe is so smooth and uniform, and it predicts that this violent expansion should have shaken space-time, creating a sea of primordial gravitational waves. The Janus point model, however, explains the uniformity differently and predicts these specific gravitational waves shouldn't be there. Our ongoing search for the faint signature of these waves in the afterglow of the Big Bang could one day tell us which picture is right. The absence of a signal could be the strongest clue yet that we aren't alone, but are part of a cosmic twinship. We're left with a profound, humbling thought. Our entire experience of a single, forward-moving timeline might just be a local perspective. The universe may not be one story, moving from a beginning to an end, but a grand novel with two tales, starting in the middle and branching out in perfect, mirrored symmetry. The cosmic story may not be about a slow decay into chaos, but about an eternal blossoming of complexity in two opposite directions. So the next time you watch steam rise from your coffee, just an everyday act of entropy, ask yourself, are you watching the future unfold? Or are you just seeing your side of a perfect, cosmic mirror? Your brain is the reason time only moves forward. You know this is impossible. Your brain instantly, instinctively, recognizes that time just doesn't work this way. Broken things don't fix themselves. Scrambled eggs don't unscramble. The past is the past. But here's the unsettling idea. The fundamental laws of physics that govern every single atom in that glass work perfectly, whether time runs forwards or backwards. The equations of gravity, of electromagnetism, of quantum mechanics, they don't have a preferred direction. A movie of planets orbiting a star looks just as plausible in reverse. So, if the universe, at its most basic level, doesn't seem to care which way time flows, why do you? Why do you only experience it as a relentless, one-way journey from a past you can remember to a future you can't? The secret, the answer to one of the biggest mysteries in science, isn't out there in the cosmos. It's in here. Inside your own head. The physics mirror. Let's start with a simple observation. If you watch a film of a simple physical event, say, two billiard balls colliding, and then watch it in reverse, you wouldn't be able to tell which was the original. The reversed movie looks perfectly normal. The laws governing that collision, like the conservation of momentum and energy, are completely time-symmetric. Physicists call this T-symmetry. And it's not just for billiard balls. Think about the Earth orbiting the Sun. If we recorded a year of its journey and played it backwards, we'd see the Earth moving along the exact same path, just in the opposite direction. Nothing in Newton's law of universal gravitation would be violated. The fundamental rules don't distinguish between past and future. This isn't just a quirk of classical mechanics. It runs much deeper. Even when we get to the bizarre world of quantum mechanics, it's a similar story. The Schrödinger equation, the master equation describing how quantum systems evolve, is also time-reversible. Even the world of electricity and magnetism, governed by Maxwell's equations, is almost perfectly symmetrical in time. Now, this isn't to say it's a completely clean slate. Physicists have found that the weak nuclear force, one of the four fundamental forces, does show a very slight, subtle violation of time symmetry. But for the most part, the overwhelming picture from physics is one of symmetry. The laws of physics largely allow for that shattered glass to reassemble itself. So why don't we ever see it happen? Why is our lived reality so profoundly, so stubbornly, irreversible? If the score of the orchestra of reality can be played forwards or backwards, why do we only ever hear the symphony in one direction? This is the great puzzle. The laws of physics might be time-symmetric, but the universe we experience is not. So where does this asymmetry, this arrow of time, come from? The first and most common answer takes us from the tiny world of particles to the grand scale of the cosmos. It's a concept you've probably heard of, but it's also one of the most misunderstood ideas in all of physics. Entropy. The universe's one-way street. Imagine you pour a drop of milk into a cup of black coffee. You watch as the white swirls and billows, slowly mixing until the entire cup is a uniform, light brown. You've just witnessed the arrow of time in action. Now, imagine waiting for that coffee to spontaneously unmix itself, for the milk to gather back into a single, pristine drop. You'd be waiting forever. It's never going to happen. This is a demonstration of the second law of thermodynamics. It's the one major law of physics that does have a direction of time built right into it. The law states that in a closed system like our universe, a quantity called entropy will always increase over time. It never, ever decreases. But what is entropy? It's often described as disorder or chaos, but a better way to think about it is in terms of probability. Think about the coffee cup. There are an astronomical number of ways to arrange the milk and coffee molecules so they're all mixed together. But there are far fewer ways to arrange them so that all the milk molecules are huddled together in one neat little drop. The universe, just by playing the odds, will always move from less probable states to more probable states. It moves from order to disorder. An intact egg is an ordered state. A scrambled egg is a disordered one. There are vastly more ways for the atoms in a glass to be scattered in pieces on the floor than there are for them to be arranged in the perfect structure of a cup. So, when you drop a glass, it shatters. It's not that the laws of motion forbid it from reassembling. It's just that it's so astronomically, laughably improbable that it will never happen. This relentless increase of entropy gives time its arrow. Physicist Sean Carroll calls this the past hypothesis. The reason we have an arrow of time is because the universe began in a very, very special state. About 13.8 billion years ago, at the Big Bang, the universe was in an incredibly low entropy state. It was extremely ordered. Ever since then, it's been unwinding and becoming more disordered, like a cosmic clock slowly running down. The future is simply the direction of higher entropy. The past is the direction of lower entropy. This is a powerful and elegant explanation. It connects our everyday experience of time's flow to the very origin of the cosmos. But there's a subtle and profound piece of the puzzle that entropy alone doesn't quite solve. The second law explains why events happen in a sequence, why yesterday is different from tomorrow. But it doesn't fully explain why we experience this sequence as a flow. It describes the track, but not the train of consciousness running on it. For that, we have to stop looking at the stars and start looking inside ourselves. Because a huge part of the story isn't just about thermodynamics. It's about memory. The turn inward. So, the universe has a one-way street defined by increasing entropy. But what if the real key to how we feel time isn't out there, but in here? What if the arrow of time is not something we just observe, but something we help create? Let's try a thought experiment. Imagine that by some unbelievable statistical fluke, the universe starts to evolve in reverse. Entropy begins to decrease. Stars reform from cold gas, and our shattered glass on the floor leaps up and reassembles itself. In this time-reversed universe, the fundamental laws of physics would still work. But what would it feel like? Would you suddenly feel like you were traveling backward in time? The astonishing answer is no. You wouldn't notice a thing. In fact, you would still feel time flowing forward, just as you do now. The direction you call forward would simply have flipped along with everything else. And the reason for this lies in the most intimate process of your conscious mind: making a memory. The footprints of yesterday. What is a memory? It's not a ghost. It's a physical thing. Every memory you have, what you ate for breakfast, your first kiss, exists as a concrete, physical structure inside your brain, a specific pattern of connections between your neurons. It's a trace, an imprint. Think of it like leaving footprints on a sandy beach. The sand in its natural state is disordered, or high entropy. When you walk across it, you create an ordered, structured pattern. The footprints. They're a record, a piece of information about a past event. To create that record, you had to expend energy, pressing the sand and releasing a tiny bit of heat, which increased the overall entropy of the beach. The creation of a record, a memory, is a process that creates a little bit of local order, the footprint, at the cost of increasing the total, global disorder, the expended energy. This is what happens in your brain. Forming a memory is a biological process that requires energy. Your brain synthesizes proteins and strengthens synapses to encode information. These are thermodynamic processes that increase the overall entropy of you and your environment. A memory is a physical record, and its creation is an irreversible process. You can't unform a memory to get the energy back, just like you can't unburn the calories you used to walk across the beach. So how does this connect to time's arrow? We think of the past as the direction from which we have records. We have memories of the past. We have footprints, photos, and neurological traces. The future is the direction where we have no records. It's a blank slate. Your brain is a memory-making machine, constantly turning the present into a physical record. This act of recording can only happen in one direction, the direction of increasing entropy. Your conscious experience is, in a way, riding the wave of this irreversible process. The flow of time you feel is the continuous, entropy-increasing process of your brain laying down memory tracks. The psychological arrow of time is locked to the thermodynamic arrow of time because the very mechanism of your consciousness memory is itself a thermodynamic process. So, in our time-reversed universe, where global entropy is decreasing, all thermodynamic processes would run backwards. And inside your brain, memories wouldn't be formed, they would be erased. From your subjective viewpoint, you would experience the process of records being created as your forward. You wouldn't feel like you were losing memories. You would feel like you were gaining them from what we, on the outside, would call the future. When the shattered glass reassembled, your brain would be forming the memory of a glass breaking. Cause would still appear to precede effect. Your subjective arrow of time points in the direction of increasing entropy for your brain, and in this case, that would be the direction the rest of us call backward. You'd be completely blind to the flip, because you are part of the flip. The conscious cosmos. This all points to a mind-bending possibility. The arrow of time, as we experience it, might not be a fundamental property of the universe, but an emergent property of consciousness itself. There's an idea in physics that stems from Einstein's theory of relativity called the block universe. It suggests that time is just another dimension, like length, width, and height. All of time, every moment from the Big Bang to the universe's end, exists simultaneously and is equally real. The past, present, and future are all just laid out in a static, four-dimensional block. If this is true, then where does the flow come from? The idea we've been building toward is that the flow is an illusion, created by how our consciousness interacts with this block. Our minds are like a spotlight moving along this 4D block, illuminating one slice at a time, which we call the present. And what determines the direction the spotlight moves? The irreversible, entropy-increasing process of forming memories. We perceive a flow from past to future because we are beings that accumulate records. Without a memory-making observer, the distinction between past and future might be meaningless. An event is in the past only if something, somewhere, holds a record of it. This is the ultimate observer effect. Our very presence as conscious, remembering beings may be what illuminates a direction in time. We are not just passive passengers on a river of time. We are, in a sense, creating the current for ourselves. The arrow is not a feature of the territory, but a feature of the map we're forced to draw as we explore. You remember yesterday and not tomorrow because remembering is a physical process that must obey the second law of thermodynamics. And that law is anchored to the fact that our universe began in an incredibly ordered state 8 billion years ago. So, in an unbroken chain of cause and effect, your inability to remember tomorrow is physically and directly linked to the conditions at the birth of the universe. What we're left with is a picture of reality that is both deeply strange and profoundly intimate. The relentless march of time, the feeling of moments passing and being lost forever, isn't some cruel joke played by the universe. It is the very price of existence. It is the engine of change that allows for complexity, for life, and for consciousness to emerge. Without the arrow of time, without the steady increase of entropy, nothing would ever happen. The fact that you can think, that you can learn, that you can remember the love and the loss and the beauty of your life, is because your brain is a small, localized system creating islands of order we call memories, all while paying the universe's tax by releasing heat and contributing to the overall disorder. Your existence is a temporary, beautiful pattern that has emerged on the universe's long journey from order to chaos. And this leads us to the final, lingering question. If the asterisk feeling of time's flow is a product of memory, and memory is a physical process, what does that say about us? It suggests that our deepest sense of reality, the forward-moving story of our lives, is tied directly to the fundamental laws of the cosmos, all because we are creatures who remember. The physics glitch forbidding time from reversing. At the most fundamental level of reality, time doesn't really exist. It's a ghost in the machine, a concept our minds cooked up to make sense of the world, but one the universe itself seems to ignore. Picture a simple collision between two particles, a tiny dance choreographed by the laws of physics. Watch it play out. Now, watch it again, but in reverse. According to our best and most profound theories, both versions forward and backward are completely valid. The underlying laws of physics don't favor one direction over the other. They have no preference for past or future. There is absolutely nothing in the rulebook that says the reversed video can't be the real one. So why does that feel so deeply, intuitively wrong? Why is our entire existence built on events that are brutally, undeniably one way? You've seen an egg fry, but have you ever seen one unfry? You've seen a building demolished, but have you ever seen a pile of rubble spontaneously leap up and rebuild itself? We remember yesterday, but we have no memories of tomorrow. It's a cosmic paradox. The rules that govern the tiniest bits of matter are perfectly symmetrical in time, yet the world they build, the world of stars, planets, and people, is relentlessly, stubbornly one-sided. It's as if the universe is running on a flawless piece of code that allows for movement in any direction, but we're experiencing a bizarre glitch, one that has locked our reality onto a single, irreversible path forward. This isn't just a philosophical puzzle. It is one of the deepest mysteries in all of science. There's a glitch in the physics of our universe, a statistical cheat, a loaded die that forbids time from ever really going backward. And to understand it, we have to uncover the most lopsided game of chance in the cosmos. The glitch. A universe with time amnesia. To really feel the weight of this problem, we need to look closer at the engine of reality, the laws of physics. For centuries, we've been writing down the rules of the universe in the language of math, and in doing so, we've stumbled upon a shocking and persistent feature. Let's start with the basics. The physics of our everyday world, like Isaac Newton's laws of motion. Imagine you toss a ball in the air. It follows that perfect, parabolic arc, up and then down. If you filmed that and played it in reverse, the ball would trace the exact same path. An object, unfalling, back into your hand follows the same mathematical rules as the initial throw. Ignoring air resistance, you couldn't tell the difference. The equations work beautifully forwards or backward. Physicists call this time reversal symmetry, or T-symmetry. And this isn't just a quirk of old-school physics. When we dive deeper, this symmetry holds. James Clerk Maxwell's equations, which describe how light waves travel, are also time-symmetric. A light wave traveling from a star to your eye is described by the same physics as a hypothetical wave converging from all of space back onto that star. The math just doesn't care. Okay, but what about the truly fundamental level, the quantum realm? Surely, this is where we'll find the source of time's arrow. But we find the opposite. The Schrödinger equation, the master rulebook for quantum mechanics, is also time reversible. The dance of particles, their interactions, their decays. Just about all of it can be run backward without breaking the laws of physics. Now, physicists have found a tiny exception involving the weak nuclear force, which does show a slight directional preference. But this effect is incredibly subtle and has virtually no impact on the macroscopic world we experience. For almost everything that matters in building our reality, the subatomic world is a two-way street. So here is the chasm, the great paradox. On one side, you have the building blocks of reality: particles, waves, forces. Their rulebook is overwhelmingly time-symmetric. On the other side, you have the world they build: galaxies, stars, and us. Our reality is governed by the arrow of time, a one-way street from past to future. This is what makes something as simple as a glass falling and shattering so profound. The glass sits on the table, a single, ordered object. It falls, hits the floor, and explodes into 1,000 pieces. We have never, not once, witnessed 1,000 shards of glass spontaneously leap together, reassemble, and fly back onto a table. Yet, if we tracked every single atom in that process, their individual collisions would all be perfectly reversible according to the laws of physics. Why don't we ever see milk unmix from coffee? Why doesn't the heat from a lukewarm mug gather itself from the cold air and heat the liquid back up? This contradiction is at the heart of our existence. Our memories are records of past events, of states that were more ordered. We remember the glass before it broke, not after. This psychological arrow of time, our very experience of life, is tied to this physical arrow. It's like the universe's fundamental parts have amnesia, they don't know which way time is supposed to flow. Yet, together, they conspire to create our unbreakable, forward-marching reality. The laws themselves don't provide the arrow. So where does it come from? The glitch isn't a flaw in the code, it's a feature. A feature born not from some new force, but from the brutal, unyielding logic of statistics. The universe isn't forced to move forward in time. It's just that moving forward is the most overwhelmingly probable thing it can do. The rigged game. Probability becomes law. The culprit behind time's one-way journey has a name. The second law of thermodynamics. And its key ingredient is a concept called entropy. You've probably heard entropy described as disorder or chaos. That's a decent starting point, but it's like calling a whale a big fish. It misses the deeper, more beautiful truth. To really get entropy, stop thinking about disorder and start thinking about possibilities. Entropy isn't a measure of messiness. It's a measure of the number of ways a system can be arranged. The more ways there are to arrange something, the higher its entropy. This idea came from the mind of Ludwig Boltzmann, a 19th-century physicist who realized that the world we see is just the statistical outcome of countless microscopic parts. Let's make this real. Imagine a box with a divider down the middle. On one side, you have 1,000,000 bees packed together. This is a low entropy state. Not because it's tidy, but because there are relatively few ways to arrange all 1,000,000 bees in just one half of the box. Now, you lift the divider. The bees, buzzing around randomly, start to fill the whole box. Soon, they're spread out more or less evenly. This is a high entropy state. The reason isn't that some force called chaos pushed them apart. It's just simple probability. Think about it. The number of ways you can arrange 1,000,000 bees so that they're all crammed into the left half is huge, but it is nothing compared to the number of ways you can arrange them throughout the entire box. For every single arrangement that looks ordered, there are an astronomical number of arrangements that look spread out. Is it possible for all the bees to spontaneously fly back into the left half? Yes. But it is so mind-bogglingly improbable that you would have to wait trillions of lifetimes of the universe to see it happen. The system moves to higher entropy not because it's being pushed, but because it's simply wandering into the state with the most possible arrangements. It's stumbling into the most probable outcome. This is the secret of the second law of thermodynamics. It's not a fundamental rule like gravity, it's a statistical one. Things go from order to disorder because there are just overwhelmingly more ways to be disordered than to be ordered. The air molecules in the room you're in right now are a perfect example. Why don't they all suddenly rush into one corner, leaving you in a vacuum? There's no force stopping them. It's because the number of ways the molecules can be arranged in the corner is infinitesimally small compared to the number of ways they can be spread evenly through the room. The odds are so vanishingly low, we can confidently say it will never happen. The universe is the ultimate statistical system. A broken glass has higher entropy than a whole one because there are vastly more ways for its atoms to be arranged as a pile of shards than a perfect glass. A coffee with milk mixed in has higher entropy because there are more possible configurations for the molecules when they're all jumbled together. This is why time has a direction. The universe is constantly exploring its possible arrangements, and it naturally wanders into the ones that are most numerous. The forward march of time is the universe simply settling into its most likely state. This is the thermodynamic arrow of time. Boltzmann formalized this with his famous equation, S equals K log W. S is entropy, and W is the number of ways a system can be arranged. All it says is that as the number of possibilities, W, goes up, so does the entropy, S. Sadly, Boltzmann's idea that a fundamental law of nature could be just a matter of statistics was so radical that he faced relentless opposition from the scientific community. The constant rejection contributed to his depression, a tragic end for the man who solved one of nature's greatest riddles. But he was right. The second law is the most stubborn law in physics. It's why you can't build a perpetual motion machine and why you can't unscramble an egg. It's not a force, but a cold, hard fact of probability. The universe is a casino where the dice are unimaginably loaded. And while it's technically possible to roll 1 trillion snake eyes in a row and see a glass reassemble itself, it is so statistically hopeless that it will never happen. The arrow of time isn't a physical leash. It's a statistical landslide. The source code, the universe's original sin. So, we have our answer. Time moves one way because the universe moves from a state of low entropy to high entropy from order to disorder. This explains why things break and never unbreak. Mystery solved, right? Not quite. In solving one puzzle, we've uncovered a much deeper one. For entropy to always be increasing, it must have started from a state of incredibly low entropy. For a ball to roll downhill, it has to start at the top of the hill. For the universe to be getting messier, it must have begun in a state of unbelievable, pristine order. This is the ultimate question. Why was our universe born with such a special, orderly past? The answer is buried at the very beginning of everything, the Big Bang. About 13.8 billion years ago, our entire observable universe was crammed into a hot, dense point. Now, you'd think a hot, violent soup of particles would be the definition of chaos, of high entropy. But you'd be wrong. The early universe was, in fact, a state of miraculously low entropy. To get this, we have to add one key ingredient: gravity. In a box of gas, a smooth, uniform spread is a high-entropy state. It's the most probable. But in a universe ruled by gravity, the exact opposite is true. Gravity pulls things together. Over cosmic time, it makes matter clump up. So, a smooth, uniform cloud of matter is actually a very unstable and statistically improbable state. It is a state of low gravitational entropy. The Big Bang started the universe in precisely that smooth, uniform, hot, dense state. It was the ultimate low entropy condition. It was a perfectly coiled spring, holding an immense potential for structure to form as it unwound. The arrow of time was set in that first moment. The entire history of the cosmos, the formation of stars and galaxies, the birth of planets, the evolution of life, and every irreversible event you've ever witnessed is just a consequence of the universe unwinding from that one special, highly ordered beginning. Our arrow of time is a cosmic inheritance, passed down from the Big Bang. We experience time moving forward because we live in a universe that is still unfolding from its pristine initial condition. This leads to some wild possibilities. What if the Big Bang wasn't the true beginning? Some physicists speculate it could have been a point of minimum entropy, with time flowing away from it in two opposite directions. That would imply a mirror universe, where time runs backward from our perspective. For anyone living there, their entropy would also be increasing from the same starting point, and they would feel time moving forward. And while the second law seems absolute for you and me, recent experiments have shown it can be briefly violated on the quantum level. Scientists have created systems where heat has been observed flowing from a cold particle to a hot one, a tiny, fleeting reversal of time's arrow. These experiments don't mean we can unscramble an egg, but they prove that entropy is a game of probability, not an ironclad command. But these are just tiny exceptions that prove the overwhelming rule. The grand, universal arrow of time points in only one direction, away from the ordered past and toward the messy future. The glitch, forbidding time from reversing, isn't a bug in the laws of physics. Those laws are time-symmetric. The glitch is in the universe's starting conditions. The source code of our reality began with one inexplicable line: start with minimum entropy. We started with a simple paradox. The fundamental laws of physics don't care about the direction of time, but our universe clearly does. We've gone from the reversible dance of tiny particles to the irreversible shattering of a glass, and all the way back to the dawn of time itself. And what we've found is that the arrow of time isn't some fundamental law. It's an emergent property, born from the simple math of probability. Time has a direction because the universe is on a one-way trip from an incredibly unlikely state of order to a state of overwhelming chaos. It's not a force pushing us forward, it's just the relentless tide of statistical likelihood. The ultimate reason for this journey, the source of this physics glitch, is the most mysterious fact about our cosmos. The Big Bang was an event of extraordinarily low entropy. The universe was born in a state of perfect order, and it has been getting messier ever since. Every cooling cup of coffee, every memory you form, every shattered glass is just a ripple from that one improbable beginning. And that leaves us with the final, and perhaps greatest, mystery of all. We can explain the arrow of time by pointing to the Big Bang. But we can't explain the Big Bang. Why did our universe begin in that one special, low-entropy state, out of all the infinite possibilities? Why was the cosmic spring coiled so tightly at the very beginning? That question remains one of the deepest, unanswered puzzles in science, a reminder that every time we solve one cosmic mystery, we find an even bigger one waiting for us. Title: Scientists discover a region of space where time runs backwards. What if the arrow of time isn't a universal law? What if, in a distant corner of the cosmos, time flows not forwards, but backwards? It sounds like pure science fiction. But what if I told you that the first hints of this reality weren't found by a telescope, but inside the deepest equations of our most fundamental physics? And what if a recent quantum experiment has, in a very real, though microscopic way, reversed the evolution of a particle, forcing us to ask, could this happen on a cosmic scale? Now, let's be very clear. No astronomer has discovered a galaxy where time is running in reverse. The title of this video is a nod to a fascinating theoretical discovery. Physicists are now seriously exploring models where the Big Bang wasn't a beginning, but a bridge to a mirror image cosmos where all the clocks run upside down. This idea, that our universe might have a time-reversed twin, is no longer being dismissed out of hand. We are on the verge of a potential paradigm shift in our understanding of reality. One that doesn't just rewrite the future, but fundamentally changes our conception of the past. Today, we journey into this mind-bending concept. We'll explore the deep mystery of why time has an arrow at all, and then venture into the speculative yet mathematically sound theories that suggest this arrow isn't absolute. This is the story of the asterisk idea of an anti-universe, of a cosmos where time could run backwards. Before we dive into the abyss, let's start with a simple question. Why do you remember yesterday, but not tomorrow? It sounds almost childish. Things move forward. You can't unbreak an egg. Smoke doesn't flow back into a cigarette. This forward march, from past to future, feels like the most fundamental rule of existence. We call it the arrow of time. But here's the unsettling secret at the heart of physics. For the most part, the basic laws don't care about this arrow. If you watch a video of two billiard balls colliding, the event looks just as plausible whether you play it forwards or backwards. The same is true for planets orbiting a star. Run the film in reverse, and the laws of gravity are perfectly happy. This principle, known as time reversal symmetry, or T-symmetry, holds for nearly all of the fundamental forces. At the micro level, the laws of physics are a two-way street. Yet, our reality is a one-way highway. So where does this unbreakable arrow of time come from? If the fundamental rules don't forbid it, why can't we rewind our own lives? This isn't just a philosophical puzzle, it's one of the deepest mysteries in cosmology. And the search for an answer is leading scientists to a possibility more shocking than the problem itself. That perhaps, on the grandest scale, time doesn't have a single direction at all. The unbreakable arrow. To understand how time might be reversed, we first need to grasp why it moves forward. Think about your desk. Over a week, it naturally gets messy. Papers pile up, coffee mugs appear. It takes effort and energy to tidy it. It never spontaneously cleans itself. This simple analogy is a window into one of the most powerful laws in the cosmos, the second law of thermodynamics. This law states that in any closed system, the total amount of disorder, or what physicists call entropy, will always increase over time. An egg is a beautifully ordered, low-entropy object. When you crack and scramble it, its molecules rearrange into a much more disordered, high-entropy state. The structure is gone. The universe will never conspire to rearrange those molecules back into a perfect, raw egg, because the number of ways for an egg to be scrambled is astronomically higher than the number of ways for it to be whole. The universe, playing a game of cosmic probability, always moves toward the most likely state: disorder. This relentless increase of entropy is the thermodynamic arrow of time. It's why coffee cools, stars burn out, and we age. We remember the past because it was a lower entropy state. We don't remember the future because it's a more disordered state that hasn't been configured yet. But this powerful explanation presents an even deeper mystery. If the universe is always getting messier, it logically means it must have started in an unbelievably tidy, low-entropy state. Think about that. The Big Bang, the most violent event we can imagine, was also a moment of near-perfect order. Why? Why did our universe begin with this exquisite, improbable order? This question, known as the past hypothesis, is a foundational puzzle. For decades, physicists have largely accepted it as a starting condition you just have to accept. But a new generation of theorists is asking, what if it's not a given? What if this low-entropy beginning is actually a clue, pointing to a much larger, more symmetric, and far stranger cosmic structure? The crack in the mirror. The world of subatomic particles is where our common sense breaks down. Here, physicists discovered a set of fundamental symmetries. We've talked about T-symmetry, time. The other two are charge conjugation. C-symmetry, which says swapping a particle with its antiparticle shouldn't change the physics, and parity, P-symmetry, which says the laws of physics should be identical to their mirror image. For a long time, these were thought to be unbreakable. But in the mid-20th century, experiments showed that the weak nuclear force violates both C and P symmetry. Nature, at a fundamental level, can tell the difference between left and right, and between matter and antimatter. This was shocking, but it led to something more profound. Physicists believe the combination of all three CPT symmetry is absolutely unbreakable. CPT symmetry states that if you take any physical process, swap particles for antiparticles, C, view it in a mirror, P, and run it backward in time, T, the resulting process must be a valid, physically possible event. Captain symmetry is bedrock for modern physics. And this is where our story takes a dramatic turn. Some physicists have proposed applying this principle to the entire cosmos. Our universe is filled with matter, a clear violation of C symmetry. So, if Captain is to hold true for the universe as a whole, this C violation might need to be balanced by a T violation. This is a speculative leap, not a foregone conclusion. But it opens up a startling possibility that our matter-dominated, forward-in-time universe might have a partner in antimatter-dominated, backward-in-time universe to keep the cosmic books balanced. This is the crack in the mirror of time. The idea that our Big Bang wasn't a singular event, but perhaps a point of transition. Not a beginning, but a center. The Janus point. A universe and its twin. The Roman god Janus had two faces, one looking to the past, the other to the future. It's a fitting name for a radical theory from physicist Julian Barbour called the Janus point. Barbour asks us to reimagine the Big Bang not as a moment of creation from nothing, but as a Janus point. A moment of minimum complexity and maximum order. From this single point, the theory proposes that the universe evolves in two opposite directions of time. On one side, you have our universe. It expands, gravity forms complex structures like galaxies and stars, and its overall entropy increases, creating the arrow of time we experience. But on the other side of the Janus point, another universe expands away from that same ordered moment. To any observer there, time would also feel like it's moving forward as their entropy increases. But from our perspective, their universe is evolving backward in time. Their future is our past. The two universes are like two rivers flowing from the same spring in opposite directions. This is an elegant idea. It tries to solve the great mystery of the past hypothesis why our universe began with such low entropy. In this model, a low entropy beginning isn't a mystery, it's the natural midpoint of the whole system. The theory also suggests that our matter-dominated universe could be balanced by a twin universe dominated by antimatter. It's important to say this is a theoretical proposal and is not yet mainstream cosmology. But it's a mathematically coherent idea that tackles some of the deepest questions in physics with a startling symmetry. Bouncing cosmology and the cosmic rewind. The Janus point isn't the only idea that allows for a reversal of time's arrow. Another set of theories, known as bouncing cosmology's arrives at a similar place from a different angle. The standard Big Bang model begins with a singularity, a point of infinite density where our physics breaks down. Bouncing cosmologies try to avoid this. In these models, the Big Bang was a bounce. There was a previous universe that contracted, heading for a big crunch. But instead of collapsing into a singularity, quantum gravity effects could have caused it to rebound, starting a new phase of expansion our universe. So where does the arrow of time fit in? The provocative proposal is that the arrow of time could be tied to whether the universe is expanding or contracting. During the expanding phase, R's entropy increases, and time moves forward. But some models suggest that during the contracting phase, the arrow of time might reverse. Entropy would decrease from our point of view. For anyone living in that contracting phase, time would still feel like it was moving forward from their Big Bang, our big crunch. But from our perspective, their clocks would be running backward. This idea finds some theoretical support in frameworks like the Hartle-Hawking no-boundary proposal. Proposed by James Hartle and Stephen Hawking, it uses quantum mechanics to describe the universe's birth, opening the door to possibilities where time's arrow isn't absolute. Like the Janus point, it's crucial to understand these are speculative areas of research with no direct observational evidence. Time in the quantum realm. So far, we've been talking about grand theories. But what about the claim that scientists have actually made time run backward? Well, it has happened, just not in the way you might think. The discovery was made in a lab, at the scale of single particles. In recent years, physicists have conducted mind-bending quantum experiments. They have managed to reverse the time evolution of a quantum state. It's like hitting a quantum undo button. By precisely manipulating a particle, they can make it return to the exact state it was in a moment before. Now, let's be crystal clear about what this means. This is not time travel. No information from the future was sent to the past. The scientists in the lab still aged forward. What they did was demonstrate that the arrow of time, for an isolated quantum system, isn't absolute. It can be manipulated. These microscopic experiments are profoundly significant. They are the first empirical evidence that the forward march of time isn't an unbreakable law, but more of a statistical reality that emerges on large scales. If time's arrow can be bent on the smallest scales, it makes the idea that it could be different on the largest scales seem less like fantasy and more like a possibility we must take seriously. What would a backward time universe look like? Let's indulge in some informed speculation. If a twin universe exists where time runs backward, what would it actually be like? From our perspective, it would be a wonderland of impossibilities. We would see stars collapsing into clouds of gas, not being born from them. Galaxies would unwind. On a hypothetical world, ruins would assemble themselves into cities, and people would emerge from the ground old and grow younger. But here is the most profound part. For the inhabitants of this universe, everything would seem completely normal. Their psychological arrow of time would be aligned with their thermodynamic arrow of time, the direction of increasing entropy in their frame. They would see their universe expanding from a big bang. They would see stars being born and dying, and themselves being born young and growing old. They would call our universe the backward one. Could we communicate? Almost certainly not. The two universes, born of the same event, would likely be forever causally disconnected, each an island of reality flowing in its own temporal stream. The only potential hint we might ever have could come from subtle clues left in the cosmic microwave background or the behavior of certain particles. The search is a long shot, but if found, it would be one of the greatest discoveries in history. We have traveled from our familiar experience of time to the deepest frontiers of modern cosmology. We've seen how a simple question, why do we remember the past, can lead to theories of a twin universe made of antimatter where the clocks run in reverse. It's a testament to how much we still have to learn. So, I have a question for you. If you could peek into this theoretical backward time universe, knowing you could never interact, what would you most want to see? The unmaking of a civilization? The unbirth of a star? Share your thoughts in the comments below. And if you enjoy wrestling with these grand cosmic mysteries, consider subscribing and hitting that notification bell. It helps us continue to bring these incredible ideas to light. Today we went looking for a place where time runs backwards. And we found something far more profound. A theoretical possibility embedded in the very laws of physics. We started with the mystery of time's arrow, sourced from the relentless march of entropy. But that led to the puzzle of our universe's impossibly ordered beginning. This is where we explored radical ideas like Julian Barber's Janus point and bouncing cosmologies, where our universe is just one side of a cosmic coin. The other side could be an anti-universe, a CPT reflection of our own, where the river of time flows in the opposite direction. The discovery, then, isn't an astronomical object. It's the realization among some physicists that our universe may be incomplete as we see it, and that time's arrow may not be fundamental, but a local perspective in a much grander, time-symmetric reality. So, the next time you watch a glass shatter, remember the possibility that, beyond the horizon of our perception, the laws of physics might permit a perfect mirror image. A cosmos where shards of glass leap back together, and time's river flows not to the sea, but forever backward, toward its own beginning. Black holes are why time only moves forward. We all know that time moves in just one direction. You can't unbreak an egg or unburn a log. A glass might shatter on the floor, but you'll never see the pieces leap back into your hand, perfectly reassembled. We get older, never younger. This one-way street for time is so fundamental to how we experience reality that we rarely even think to question it. Scientists call it the arrow of time. But have you ever really stopped and asked why? Why is time so stubborn? This isn't a philosophical question, it's one of the biggest puzzles in physics. Because the strange truth is, most of the fundamental laws of nature don't forbid time from flowing backward. The equations that govern everything from the dance of planets to the collision of atoms work just as well in reverse. If you watched a video of a planet orbiting a star, you wouldn't be able to tell if it was playing forwards or backward. Both would look completely normal. So, if the tiny, microscopic rules don't care about the direction of time, what's enforcing this strict, one-way-only rule for the rest of us? What cosmic law says yesterday is gone forever and tomorrow is always yet to come? The answer isn't on Earth, or even in our solar system. The answer lies in the darkest, most extreme, and most mysterious objects in the entire cosmos: black holes. They aren't just cosmic vacuum cleaners. They're the universe's timekeepers. The great cosmic mystery. The arrow of time. To understand what black holes have to do with anything, we first have to appreciate the mystery they solve. It's a mystery born from a deep contradiction. On the one hand, you have your own experience. Every moment of your life reinforces the idea that time moves forward. You make memories. You don't unmake them. You anticipate the future. You don't remember it. This feeling that we're moving from a fixed past into an open future is absolute. It's the foundation of cause and effect. A cause has to come before its effect. You throw a ball, then it hits a wall. Never the other way around. But when physicists look at the fundamental machinery of the universe, this arrow just vanishes. The laws of motion from Newton, the laws of electromagnetism from Maxwell, even the bizarre quantum rules worked out by pioneers like Schrödinger and Heisenberg, at their core, they are all time symmetric. The math doesn't have a built-in forward button. A physical process and its time-reversed twin are equally possible. Imagine filming two billiard balls colliding. You see the cue ball hit the 8 ball, transferring its momentum as they both scatter. Now, play that film in reverse. You'd see the scattered balls roll back toward each other, collide, and the cue ball would recoil while the 8 ball stops dead. It would look weird, sure. Improbable, definitely. But according to the laws of motion, nothing about it is impossible. So why doesn't this happen in real life? Why don't we see smoke pouring back into a fire or scrambled eggs separating back into yolk and white? Why is the big world we see and touch so different from the microscopic world it's built on? This is one of the deepest questions in science. It tells us that our sense of time's flow doesn't come from the basic rules. It must be an emergent property, something that pops up from the collective behavior of trillions upon trillions of particles. It's a statistical game. And the science that governs this game, the science that finally gives time its direction, is thermodynamics. The answer to why does time move forward isn't about motion or gravity. It's about order, disorder, and the universe's unstoppable march towards chaos. The answer is a single word: entropy. The prime suspect, the law of entropy. Entropy is a word that gets thrown around a lot, usually as a stand-in for messiness. But it's much more specific than that. To really get why time moves forward, we have to get what entropy really is. Let's try an analogy. Think about your bedroom. There are only a handful of ways for your room to be clean. The books are on the shelf, alphabetized. The clothes are in the closet, folded. The bed is made. It's a very specific, low probability state. Now, think about how many ways your room can be messy. The books could be in a pile on the floor. The clothes could be, well, anywhere. There aren't just a few ways for it to be messy. There are millions, maybe billions of possible arrangements that all count as messy. Scientifically, that's what entropy measures. It's the number of different ways you can arrange the atoms in a system that still looks the same on a large scale. A clean room has low entropy because there are very few arrangements that fit the description. A messy room has high entropy because there are a staggering number of ways for it to be messy. Or think about a deck of cards. There's only one way for it to be in perfect, new deck order. That's a state of minimum entropy. But if you shuffle that deck just once, the number of possible scrambled arrangements is astronomical, a 68-digit number. The chance of shuffling the deck and having it land back in perfect order is basically zero. It's not forbidden by physics, it's just statistically absurd. The system naturally moves from that single, ordered state to one of the countless trillions of disordered states. It moves toward higher entropy. This is the core of the second law of thermodynamics. It says that in a closed system, the total entropy will almost always increase over time. It never, ever goes down on its own. A hot cup of coffee in a sealed room will always cool down, spreading its heat energy into the air until everything is the same temperature. The initial state hot coffee, cool air is more ordered. The final state lukewarm everything is more disordered. You will never see the air in that room spontaneously give its heat back to the coffee. There are just vastly more ways for the energy to be spread out than for it to be concentrated. The universe always moves toward the most probable state, and that state is always the one with the highest entropy. This right here is the engine of time. Time has a direction because the universe as a whole has been following the second law of thermodynamics for roughly 13.8 billion years. Scientists believe the universe began in an incredibly special, highly ordered, low-entropy state at the Big Bang. Since then, it's been expanding, cooling, and getting messier. It's been on a one-way trip from that initial state of perfect order toward a future of maximum disorder. The shattering of a glass, the cooling of coffee, the process of aging, they're all just small examples of this one cosmic rule. They are all processes that increase the total entropy of the universe. The relentless increase of entropy is what separates past from future. The past is low entropy, the future is high entropy. For a long time, this felt like a complete answer. The second law of thermodynamics gave time its arrow. But then, we discovered objects so extreme, so bizarre, that they appeared to be cosmic criminals, capable of breaking this most sacred law. These objects were black holes, and they threatened the very fabric of time. The ultimate anomaly, black holes versus entropy. Black holes are the ghosts of general relativity, points where Einstein's fabric of space-time is stretched to its absolute limit. They are spots where gravity is so strong that nothing, not even light, can escape. This point of no return is called the event horizon. Anything that crosses it, a star, a planet, an unlucky astronaut, is gone from our universe forever. In the 1970s, as physicists started taking black holes seriously, they ran into a horrifying paradox. The problem was simple. What happens to the entropy of something when it falls into a black hole? Imagine a star. A star is an incredibly complex thing, a swirling ball of hot gas with fusion in its core, magnetic fields, solar flares. It has an enormous amount of entropy. Now, let's say that star gets swallowed by a black hole. From our perspective, the star just vanishes. All its complexity, all its history, and most importantly, all its entropy, seems to be erased from the universe. According to the classical physics of the time, black holes were terrifyingly simple. You could describe them with just three numbers: their mass, their spin, and their charge. That's it. There was no room in the math for the entropy of all the stuff they ate. A classical black hole had zero entropy. This was a catastrophe. If you could take a high-entropy star and throw it into a zero-entropy black hole, the total entropy of the universe would go down. This would be a direct violation of the second law of thermodynamics. And if the second law could be broken, the whole reason for the arrow of time would fall apart. Why shouldn't glass shatter if the universe's most fundamental rule could be so easily ignored by these cosmic monsters? This puzzle, which became known as the black hole information paradox, deeply bothered physicists. One of them was a graduate student at Princeton named Jacob Bekenstein. In 1972, Bekenstein had a wild idea. He was inspired by a discovery from Stephen Hawking, who had proved that the surface area of a black hole's event horizon could never decrease. When two black holes merge, the new one's surface area is always equal to or greater than the sum of the original two. Bekenstein noticed that this property "it only ever increases" sounded an awful lot like entropy. So he proposed something radical. What if a black hole does have entropy? And what if that entropy is proportional to the surface area of its event horizon? At the time, this was heresy. Most physicists, including Stephen Hawking, thought the idea was ridiculous. For a black hole to have entropy, it would have to have a temperature. And if it had a temperature, it would have to radiate heat. But everyone knew that nothing escapes a black hole. Hawking, in particular, was annoyed by Bekenstein's idea. He thought it was a sloppy misuse of his own theorem, and he set out to prove Bekenstein wrong once and for all. He started calculating what would happen if you brought the strange rules of quantum mechanics to the very edge of a black hole. What he found wouldn't just fail to disprove Bekenstein. It would lead to the single greatest discovery of his career and completely change our understanding of black holes, entropy, and time itself. The revelation. The timekeepers of the cosmos. In his effort to shut Bekenstein down, Stephen Hawking dove into the bizarre world of quantum field theory. He was looking at virtual particles. In the quantum world, empty space isn't really empty. It's a fizzing soup of particle-antiparticle pairs that pop into existence for a split second before destroying each other. Hawking wondered, what happens if a pair of these particles appears right on the edge of the event horizon? It was possible for one particle to fall in while its partner escaped. To a distant observer, it would look like the black hole had just spat out a particle. The energy to create that particle had to come from somewhere. It came from the black hole's own mass. By emitting this particle, the black hole would lose a tiny bit of weight. Hawking was floored. His own math showed that black holes weren't completely black. They should glow, ever so faintly, with thermal radiation. This, Hawking radiation, meant that black holes must have a temperature. And if they have a temperature, thermodynamics says they absolutely must have entropy. He had set out to destroy Bekenstein's idea, and instead, he proved it was correct in the most spectacular way possible. He even found the exact formula for a black hole's entropy. Just as Bekenstein guessed, it was proportional to the surface area of the event horizon. This was the solution. Black holes don't destroy entropy. In fact, they are the most entropy-packed objects in the entire universe. The amount of entropy held by a single supermassive black hole is staggering far, far greater than the entropy of the star it swallows. So let's go back to our star falling into the black hole. When the star crosses the event horizon, its own entropy might seem to vanish. But in that same moment, the black hole's mass goes up, which means the surface area of its event horizon gets bigger. The increase in the black hole's entropy is always greater than the entropy of the thing it just ate. The books are balanced. The total entropy of the universe, the stuff outside plus the black hole itself, always goes up. The second law is safe. The arrow of time is preserved. Black holes aren't the villains of this story. They're the enforcers. They are the universe's bookkeepers, making sure that the total entropy always increases. They are cosmic engines that turn ordered matter into pure, raw entropy, stored on their surface. And this is where things get truly strange. The immense gravity of a black hole doesn't just warp space, it warps time. To a distant observer, a clock falling into a black hole would seem to tick slower and slower, freezing entirely at the event horizon, its light stretching out and fading away. They'd never actually see it cross. But for the person falling in, time would feel completely normal. They'd cross the event horizon just fine. Inside, though, our concepts of space and time break down and swap roles. The direction toward the singularity, the center of the black hole, is no longer a direction in space. It becomes the future. Just as we can't stop moving toward tomorrow, an astronaut inside a black hole cannot stop moving toward the singularity. The singularity isn't a place. It's a moment in time you are destined to meet. That's why you can't get out, you can't travel backward in time. The cosmic timekeepers. We started with a simple observation. Time only moves forward. This led us to a deep puzzle, because the fundamental laws of physics don't seem to care which way time flows. The solution, we thought, was the second law of thermodynamics: the universe's total disorder, its entropy, always increases, giving time its direction. But this beautiful idea was almost shattered by black holes, which seemed to be cosmic glitches where entropy could be destroyed and the arrow of time broken. The resolution was a genuine revelation from Jacob Bekenstein and Stephen Hawking. Black holes don't destroy entropy, they are colossal containers of it. They aren't lawbreakers, they're the ultimate guardians of the second law. Every star they devour only serves to increase their own entropy, guaranteeing that the total entropy of the cosmos continues its relentless climb. Think about the opposite of a black hole. A white hole. It's a hypothetical object that does the reverse, matter can only flow out of it. While they are possible in the math, we've never seen one. Why not? Because a white hole, by spewing out matter and energy, would decrease entropy. It would violate the second law. The fact that our universe has black holes but not white holes is another powerful piece of evidence for the supremacy of time's arrow. Black holes are the final word on the direction of time. Their existence and their properties are woven into the law of increasing entropy. They are an essential part of the cosmic engine that ensures the universe has a history and a future, that causes come before effects, and that yesterday is forever different from tomorrow. So, the next time you look at a clock, ticking steadily forward, remember what it really represents. It's more than just gears and springs. It's a small echo of a vast, cosmic process. The clock is ticking forward because the universe is getting messier. It's ticking forward because somewhere in the deep darkness of space, a black hole is doing its job, growing, storing entropy, and ensuring that the story of our universe can only be written in one direction. You are now aging in reverse. You are 95 years old. And you have just died. Don't be alarmed. It was peaceful. A long, full life winding down to a quiet, expected stop. Your family was there. You felt the threads of your own story gathering into a final, satisfying knot. You closed your eyes, and your last breath escaped like a sigh. The end. But something's wrong. Instead of the great fade to black, or the brilliant white light you might have secretly hoped for, there's a sensation. A sharp, pulling feeling, like a cosmic thread has been violently yanked. Your last breath, the one that just left your lungs, hitches in your chest, and then, impossibly, you take another. It's not a gasp for life. It's an asterisk ungasp. Your eyes, which had filmed over with the finality of it all, flutter open. You're in your deathbed, surrounded by the pale, tear-streaked faces of your loved ones. But their tears aren't falling. You watch, bewildered, as a single tear defies gravity, slides up your daughter's cheek, and vanishes back into her eye. Your heart, which had fallen silent just moments ago, gives a sudden, violent lurch. It's not just beating, it's beating stronger. Aches that have been your constant companions for 2 decades begin to recede, not like a tide going out, but like a film being run in reverse. The creak in your joints, the fog in your mind, the dull weight of almost a century of existence, it's all lifting. You try to speak, to ask what's happening, but the words form backwards in your throat. Sounds retreat into your mouth. A strange glitch in the fundamental laws of the universe has just targeted you. You are not being reborn. You are not going to an afterlife. You are now aging in reverse. The first unwinding, the hours and days. The first few hours are a blur of impossibilities. The deep, settled wrinkles around your eyes, etched by 95 years of laughter and sorrow, begin to shallow. You can feel it, a strange tightening of your skin, like a clay sculpture being smoothed by an unseen hand. The liver spots on the back of your hands, which you'd long ago accepted as part of your personal landscape, fade into your skin like ghosts. Your hair, a fine, silvery white, starts darkening at the roots with an unnerving speed. Your family's grief is playing out in reverse. Sobs become sharp intakes of breath. Their faces, contorted with pain, smooth into expressions of tense anticipation. They are unsaying their goodbyes. Words fly backward from their lips into their mouths, a garbled retreat of language. You can't understand the sounds, but you feel the emotional charge of the moment rewinding. The profound sadness that filled the room is being sucked out, replaced by the frantic, anxious energy that came before your death. The doctors, who had pronounced you gone, are now in a state of clinical panic. They uncheck their watches. They unwrite notes on their clipboards, ink lifting from the page and returning to the pen. You are becoming a medical anomaly, a paradox their science cannot explain. Because the laws of physics as they know them have a direction, a rule. The second law of thermodynamics states that in an isolated system, entropy disorder can only increase. A cup of coffee cools. An egg, once scrambled, can never be unscrambled. A life, once lived, cannot be unlived. And yet, here you are. The ultimate unscrambled egg. By the next day, you're 94. The change isn't just cosmetic. A debilitating arthritis in your hip that had confined you to this bed has vanished. You swing your legs over the side, your muscles feeling not just healed, but younger, stronger. You stand, and the stoop in your back, the one that had bent you toward the earth for a decade, straightens itself out. You're an inch taller than you were yesterday. The world outside your room is a dizzying reverse ballet. Cars drive backward, exhaust fumes sucking back into their tailpipes. People walk backward, their conversations a rewind of sound. Are you a fixed point of forward consciousness in a world flowing the wrong way? Or is the world normal, and you're the one thing flowing backward against its current? It's impossible to tell. The food on your bedside table is the strangest part. A half-eaten bowl of oatmeal slowly reassembles itself. Stray oats leap from the table back into the bowl. Your body, now operating on a reverse metabolic cycle, isn't hungry. Instead, it feels the impending need to uneat. Nutrients from your last meal stream out of your cells, back into your digestive tract, preparing to reform into food that will leave your mouth and return to your plate. It's a violation of everything you know about being alive. Life consumes. It breaks down. Your body is now doing the opposite. It's giving energy back, creating order from disorder, a localized, personal defiance of one of the universe's most fundamental laws. You catch your reflection in the window. The face staring back isn't the one you went to sleep with for the final time. It's the face of you from last year. A little fuller, a little less weary. It is undeniably you, but a version you thought was lost to the past. You touch your cheek, and the skin feels supple. The overwhelming feeling isn't joy, but a profound, creeping dread. You're not just getting healthier. You're being erased. The great unlearning. The fading of a lifetime. The reversal continues, not in days, but in years. Each morning, you're younger. You mark time by the unlighting of birthday candles, by the return of forgotten strengths, by the slow, inexorable march backward through your own history. You're 85. Your husband, who passed away 10 years ago in the forward direction of time, is now alive again. One day, you simply unreceive the phone call that told you he was gone. The memory of his funeral, a scar on your heart for a decade, begins to unravel. The grief doesn't just fade. It actively disassembles. The sharp pangs of loss become a dull ache, then a sad memory, then a premonition, and finally, nothing. In your timeline, it hasn't happened yet. He's there, frail and fading toward the death you've already unwitnessed. Your relationship with him becomes a strange, inverted dance. You grow stronger as he grows weaker. You regain memories as he loses them. The conversations you have are echoes of a future you've already lived. You know his punchlines before he tells them, his fears before he voices them. But this knowledge is fleeting. This is the beginning of the great unlearning. Your mind, just like your body, is subject to this temporal glitch. The process of memory is intrinsically linked to the arrow of time. We remember the past, not the future. It starts with the recent past. The name of the nurse who helped you this morning vanishes. The plot of the book you just finished reading evaporates. Then, bigger things. You find yourself standing in a room with no idea why you're there, only to realize you are unwalking to a room you haven't decided to go to yet. The names of your great-grandchildren are the first to go. They become smiling, unfamiliar faces in photographs. Then, your grandchildren. You look at these adults who call you grandma, and the name feels alien. The deep, instinctual love you have for them is still there, a ghost in the machine, but the narrative that binds you to them is fraying. You can't remember their births, their graduations, their weddings. You are unliving these moments. Your own children are next. These middle-aged people, with their lives and worries, are becoming strangers. You love them, but the love is becoming an abstract concept, a fact without the supporting evidence of shared experience. You're losing the very memories that define you. The scraped knees you bandaged, the bedtime stories you told, the arguments you had, the pride you felt, all of it is being spooled back into the machine. The Danish philosopher Søren Kierkegaard once wrote, "Life can only be understood backwards, but it must be lived forwards." You're trapped in a terrifying, literal version of this idea. You are traveling backward, seeing the connections of your life with a clarity that is both profound and useless, because you're simultaneously losing the consciousness that allows you to understand it. You're watching the dots of your life connect in reverse, even as the you doing the watching is dissolving. Your friends, your community, your entire social fabric unravels. The friends you mourned are alive again, but you are unmeeting them. A lifetime of shared jokes, confidences, and support dissolves into polite nods with strangers you feel you should know. You're becoming isolated, not by choice, but by the relentless physics of your condition. You're an island of reverse causality in a forward-flowing world. You are becoming a ghost in your own life story. This is the central terror. It's not just losing your life, it's losing the asterisk meaning of your life, one memory at a time. Middle age in reverse. The undoing. You're 55, 45, 35. Decades peel away like layers of an onion. This is the prime of your life, lived in reverse. It's not a second chance, it's an undoing. Your career, the one you spent 30 years building, dismantles itself. Your retirement party unhappens. You give your farewell speech. You're back at your desk, but your authority is shrinking. Projects you spearheaded are unlaunched. Eventually, you unsign your initial employment contract and walk out the door for the first time, a young person full of a potential you have just finished unfulfilling. The home you shared with your family, the epicenter of your life, is unbought. Movers come and pack your belongings not into boxes, but out of them. You sign the mortgage papers in reverse, the ink lifting from the page. You hand the keys back to the real estate agent and drive away from the house filled with 4 decades of life, now just a structure of wood and brick you've never lived in. But the most gut-wrenching reversal is your family. Your children, who were independent adults, are now teenagers living under your roof again. The empty nest you once lamented is full, but the dynamic is inverted. They aren't growing up and away from you. They're growing younger and toward you. Their independence erodes. Their life experiences vanish. You have to parent them in reverse. You teach them how to drive. You enforce curfews they've long since outgrown. The conversations are a nightmare of reverse causality. You give them advice for problems they haven't had yet, based on a wisdom you're rapidly losing. And then there's your marriage. The comfortable companionship of old age has rewound into the turbulent passion of midlife. The vows you spoke, "till death do us part," have been rendered meaningless. The settled, quiet understanding is replaced by arguments you're now having for the first time. Old wounds, long healed, reappear as fresh cuts. You say, "I love you." Lying in bed next to your husband, you look at the man you will unmarry. The person who will become a stranger you once loved. The fights, the reconciliations, the shared dreams, all of it is a tape playing backward. The climax of your love story was its quiet, gentle end. Now you're racing away from it, back toward the explosive, uncertain beginning. The physical rejuvenation is relentless. You have the body of a 30-year-old. You're strong, energetic, free from pain. But it feels like a cruel joke. What's the use of a youthful body when your mind is being hollowed out? You're a beautiful vessel from which the essential self is being scooped. Friends who are aging normally look at you with a mix of envy and fear. They are accumulating life, gathering stories. You are shedding them. The fundamental equations of physics, like Newton's laws, are mostly time reversal symmetric. A video of planets orbiting a star looks just as valid played forward or backward. On a microscopic level, time has no preferred direction. The arrow of time we all experience is an emergent property of entropy, a statistical likelihood that disorder will increase in a complex system. You're just an impossibly unlikely statistical fluke. A system where entropy is decreasing, where order is spontaneously emerging from chaos. But this cosmic order feels like the ultimate personal chaos. It's the orderly, systematic destruction of you. Young adulthood, the unbecoming. You are 25. The weight of a mortgage, a career, and raising a family has lifted, replaced by the boundless, terrifying freedom of youth, experienced in reverse. College is an exercise in profound confusion. Instead of knowledge flowing into your mind, it flows out. You unwrite your thesis, each keystroke removing a word until you're left with a blank page. You're paying to become less educated. You walk backward across the graduation stage, the diploma is taken from your hand, and you are a freshman again, filled with a sense of impending purpose that will never be realized. The person you married is now just someone you're dating. The deep tapestry of your shared life has unraveled into a few thin threads. The first, "I love you," is taken back. The first kiss is unkissed, a moment of startling intimacy rewinding into a shy, hesitant silence. You go on your first date in reverse, ending the night as strangers who will never meet. The person who was the center of your universe is now just a face in a crowd. The pain of this is a new and terrible thing. It's not the grief of loss, but the grief of unhaving. Friendships dissolve not in anger, but in a clean, systematic unmeeting. You're at a party, and a person you have known for what feels like a lifetime walks backward out of your life, and you're left with no memory of them ever being there. Your sense of self is in freefall. An adult identity is built on a foundation of choices and experiences. Your foundation is being dismantled. You're adrift, a collection of impulses and fading echoes of a life you can no longer access. You feel the weight of responsibilities you no longer have. You feel the love for people you no longer know. You move back in with your parents. They are vibrant, middle-aged people who look at you with love and concern. You're their child again, but a strange, broken version. An adult in a young person's body, with a mind that's rapidly losing its adulthood. You're a dependent again. The people you once guided are now guiding you, and you can't remember ever being the one in charge. The world feels bigger and more confusing. The internet, once an integral part of your life, is now a strange, nascent thing you don't understand. You're becoming a stranger in time. Adolescence and childhood, the engine of innocence. You are 15. The sophisticated architecture of your adult mind has crumbled, leaving the raw, volatile emotions of adolescence. You're not growing out of this. You're growing into it. Your body is a landscape of forgotten stories. That scar on your knee from a childhood bicycle accident, a faint white line for 80 years, suddenly reappears. It tingles, then turns pink, then red and raw as it unheals. One afternoon, you feel a sharp pain as the wound reopens, and in a nauseating flash, you are unfalling off your bike, the ground rushing away as you're propelled backward into a state of perfect balance. The knee is unscraped. Your body is becoming a blank slate. School is a disorienting fog. Algebra becomes an incomprehensible series of symbols. You sit in class, feeling answers leave your mind just before the teacher asks the question. Friendships are intense and dramatic as they unravel. The high school sweetheart you once wept over now unbreaks your heart. Your parents become your entire world. The life you built, your own family, it's not even a memory now. All that exists is this house, these rules, this desperate, confusing need for their approval. You're trapped in the emotional landscape of your own childhood. You are 10. The world is a place of magic and rules you don't understand. Language begins to simplify. Your vocabulary shrinks. You lose the ability to understand sarcasm and abstract thought. You look at the world with a child's wide-eyed wonder, but it's a tainted wonder. It's the wonder of forgetting, not of discovery. You are 5. The world is a series of simple, sensory inputs. The color of the sky, the warmth of the sun, the taste of ice cream as it reforms on your tongue before you put it back in the cone. The narrative of your life has completely dissolved. There's no past or future, only a continuous, flowing river of reverse moments. Your grasp on language loosens entirely. First, you lose coherent sentences. Then, words themselves become just sounds. Mama, dada. These fundamental pillars of your world are unspoken, the sounds retreating into your infant lungs. You're in a crib. A face looms over you, a face you recognize with a deep, pre-verbal instinct. It's your mother. She is not an old woman you cared for, or a middle-aged woman you rebelled against. She is the sun, the source of all warmth and comfort. You can't think this in words, but you feel it in the core of your being. You are pure potential, but in reverse, moving toward absolute non-existence. The final forgetting. The return to nothing. You are 1 year old. The world is a kaleidoscope of light and sound, without meaning. The distinction between self and other, the first great act of consciousness, dissolves. The hand that waves before your face is no more you than the mobile spinning above your head. You are a bundle of senses, a passive observer of a film rewinding at incredible speed. The act of walking is unlearned. Those triumphant first steps are taken back. You are crawling again, but backward. Then crawling ceases. Your body shrinks. Days are years. Hours are decades. The universe of your 95-year life is collapsing back into a single point. The final wall to fall is consciousness itself. It's a process tied to the arrow of time, to accumulating experience. As your timeline rushes to its origin, the very mechanism that allows you to be an I shuts down. There is no more you. There is only a process. A biological machine running in reverse. You are in the womb. It's dark. It's warm. It's silent, save for the rhythmic, muffled beat of a heart that is not your own. The complex organism you were is rapidly deconstructing. Organs unform. Limbs retract. You are a fetus, a cluster of cells, a blastocyst. The journey reverses up the fallopian tube. You are undividing. 4 cells become 2. 2 become 1. Here, at the very precipice of being, the laws of physics deliver their final, inscrutable verdict. You are a single, fertilized egg. Then, in a flash of biological anti-causality, the egg unfertilizes. You are gone. You have not died. You have unexisted. The entire, sprawling, beautiful, tragic story of your 95 years has been perfectly and utterly erased, leaving not even a ripple in the fabric of space-time. It has all been returned to a state of pure potential. A question that was never asked. So why doesn't this happen? Why is your life, and my life, a one-way street? The fundamental laws of physics, for the most part, don't care about the direction of time. A planet could orbit its star backward and the math would still work. But our universe as a whole has a direction. An arrow. It flies from a past of incredible order toward a future of ever-increasing disorder. This is the second law of thermodynamics, the principle that entropy, or chaos, always tends to increase. A broken glass never reassembles itself because the number of ways for it to be broken is astronomically higher than the one way for it to be whole. Our lives, our consciousness, our ability to form memories, it's all built on this forward flow of entropy. Some research even suggests a link between consciousness and the brain maximizing its entropy, its configurations of neural networks. To remember yesterday, your brain must exist in a state that is more complex than it was yesterday. To live life in reverse is to move toward simplicity, toward order, toward the erasure of information. It's to move against the very current that makes experience possible. The philosopher Kierkegaard was right. We live life forward, but we understand it backward. We find meaning by looking back at the tapestry we've woven. Perhaps that is the profound, hidden beauty of our one-way existence. Our scars tell our stories. Our memories give us substance. The irreversible nature of our choices is what gives them meaning. Your life is not a reversible equation. It is a singular, unfolding story. Every moment is precious because it will not come again. Every choice matters because it cannot be unmade. You are not decaying. You are accumulating. You're a masterpiece of ever-increasing complexity, riding the arrow of time not toward erasure, but toward wonder. And in a universe that relentlessly marches toward chaos, the simple act of living, of creating memories, and of telling a story is perhaps the most profound act of rebellion there is. If you've ever felt lost in the forward march of time and enjoy exploring these kinds of thought experiments, consider subscribing. We spend a lot of time thinking about what it means to be here, now. And we'd love for you to join us. The universe's greatest mystery: why time has a direction. We live our lives by the clock. Seconds tick into minutes, minutes into hours, and the years stretch out behind us like a road disappearing over the horizon. We remember the past. We look forward to the future. A glass falls and shatters. A match burns to ash. An egg cracks and scrambles. This is the rhythm of our reality, the fundamental current that carries everything and everyone along in its flow. It feels inevitable. It feels absolute. But it's not. This one-way street we call time might just be the most profound and unsettling mystery in all of physics. Because when you peel back the layers of reality, when you inspect the very rulebook that governs every particle and force in the cosmos, that forward-pointing arrow vanishes completely. The universe, at its most fundamental level, doesn't seem to care about the difference between yesterday and tomorrow. So where does it come from? Why is our universe, and our experience in it, so fiercely, so unyieldingly directional? This isn't just a question for a blackboard. The answer is written in the stars, in the fire of the Big Bang, and in the very way you're able to form a memory of these words. This is a cosmic detective story. And we're the detectives, following a trail of clues from our kitchen tables back to the dawn of creation itself, all to uncover the secret of why time has a direction. Imagine watching a video of a teacup slipping from a table, falling, and shattering into 100 tiny pieces on the floor. Now, imagine running that video in reverse. The shards leap from the ground, magically reassembling in midair, landing perfectly back in the cup's original form, before hopping back onto the table, whole and pristine. We know this can't happen, right? Our gut, our entire life experience, screams that this is impossible. But what if I told you that according to the fundamental laws of physics, it can? The equations that govern every atom in that teacup, the laws of gravity pulling it down, the forces holding it together, they all work just as perfectly forwards as they do backwards. There's nothing in the rulebook of reality that forbids those pieces from flying back together. And yet, they never do. So, what gives? Why is our universe a one-way street? Why can we remember the past but not the future? Something, somewhere, broke the symmetry. Something forced time's arrow to fly in only one direction. And finding that something takes us on a journey to the most extreme and mysterious event in cosmic history. The very first moments of the Big Bang. The scene of the crime. Our experience of time. Before we blast off into the depths of space and time, our detective story starts somewhere much more familiar. Right here. The first step in any mystery is to examine the evidence. And the evidence for time's arrow is everywhere. Think about your morning coffee. You pour cold cream into the hot, dark liquid and watch it swirl and mix, the white clouds dissolving until the entire cup is a uniform light brown. You will never see the reverse. You'll never see a cup of coffee spontaneously unmix itself, the cream separating out into a tidy pool on the surface. Think of an ice cube melting in a glass of water. Heat flows from the warmer water to the colder ice until everything hits the same temperature. You'll never see a glass of lukewarm water spontaneously form ice cubes while the rest of the water gets warmer. Think of the sound of a bell. When you strike it, the vibrations travel outwards in an expanding sphere of sound. You'll never hear the quiet sounds of a room suddenly rush inwards, converge on a silent bell, and make it ring. This is our evidence. It's so ordinary, so woven into our existence, that we rarely stop to question it. These are irreversible processes. They go one way, and one way only. The astrophysicist Arthur Eddington, back in 1927, gave this a great name: time's arrow. He noted three crucial things about it. First, we feel it in our consciousness. Second, a world where the arrow was reversed would feel like absolute nonsense. And third, the real mystery, it's completely missing from the fundamental laws of physics. And here's the central crime scene of our whole story. We have a universe that clearly plays by a directional rule, but the official rulebook seems to be missing that page entirely. We experience a deep asymmetry in time, a bright line between past and future. Eggs break, they don't unbreak. People get older, they don't get younger. The universe moves from order to disorder. And yet, the physics running the show for every atom in that egg should allow for the reverse to happen. This gap is our first major clue. The arrow of time isn't a fundamental command like the speed of light. It's what physicists call an asterisk emergent property. It arises from something else. The question is, what? Our investigation has a starting point, and now we need a suspect. And in the world of physics, when you're talking about disorder and one-way streets, there's one prime suspect. Its name is entropy. The prime suspect, entropy and the second law. To understand time's arrow, we have to get to know our prime suspect, entropy. The word might sound a little technical, but I promise, you already get the basic idea. Entropy is just a physicist's word for disorder, randomness, or chaos. And the principle that governs it is one of the most powerful in all of science. The second law of thermodynamics. The second law states that in any isolated system like our universe as a whole, total entropy, or disorder, will always increase or stay the same. It never goes down on its own. Disorder always wins. That's the law. But law is a bit misleading. It's not a command. It's a law of statistics. It's a statement about what is overwhelmingly, astronomically probable. Let's use an analogy. It's a trick physicists love. Imagine your bedroom. There's really only one way for it to be perfectly tidy. Every book on the shelf, every shirt in the drawer. But how many ways can it be messy? A book on the floor, a sock on the chair. There are billions, countless ways for it to be disordered. If you just randomly tossed your belongings into the room, what are the chances they'd land in that one, perfectly tidy arrangement? Practically zero. Your room gets messy not because of a messy force, but because there are just vastly more ways for it to be messy than tidy. Now, let's try another. Imagine a brand new deck of cards, perfectly ordered from ace to king in every suit. That's a state of low entropy, highly specific, highly ordered. Now, shuffle them. The order is gone. The deck is now in a state of high entropy. Why? Because while there's only one way for the deck to be perfectly ordered, there are more than 8 times 10 to the 67th power ways for it to be shuffled. That's an 8 with 67 zeros after it. It is astronomically likely you will land on a disordered arrangement. It is astronomically unlikely that your shuffling will, by pure chance, put the deck back in perfect order. It's not technically impossible. But you could shuffle for the entire age of the universe, and you wouldn't even get close. And that's the real secret of the second law. The universe doesn't prefer disorder. It's just that there are colossally, unimaginably more ways for things to be disordered than ordered. Let's apply this to a box of gas. Imagine we release a puff of gas into one corner of a sealed, empty box. That's a low entropy state. All the particles are neatly contained. What happens next? The gas expands to fill the entire box. The entropy increases. Why? Because for every one way those molecules can be huddled in the corner, there are googles of ways for them to be spread out. The gas spreads out because it's just exploring possibilities, and the vast majority of those possibilities look spread out. For all those molecules to spontaneously rush back into the corner is not forbidden by the laws of motion, but it's so statistically ridiculous it would never happen. This was the genius insight of 19th century physicist Ludwig Boltzmann. The world we see of melting ice and mixing coffee is just the average behavior of a staggering number of microscopic parts. Physicists call these microstates and macrostates. A macrostate is the overall picture, like the coffee is all mixed. A microstate is the exact position and speed of every single molecule. And the key is, there are vastly more individual particle arrangements, microstates that look like mixed coffee, a high entropy macrostate, then arrangements that look like separate cream and coffee, a low entropy macrostate. So, time's arrow is simply the universe moving from rare, special, low entropy states to super common, generic, high entropy ones. It's the path of least resistance, dictated by the brute force tyranny of probability. We have our prime suspect, entropy. The reason the teacup shatters is because there are countless more ways for its atoms to be in a shattered pile than in a whole cup. The reason time moves forward is because the universe is on a one-way trip from order to disorder. But a good detective knows not to get tunnel vision. We've got our prime suspect, but now we need to check the alibis of all the other players. We need to interrogate the fundamental laws of physics themselves. Checking the alibi, the indifference of physical law. Our investigation has led us to a powerful suspect, the second law of thermodynamics. But this creates a huge paradox. The laws that govern the microscopic world, the actual rules the atoms themselves play by, are almost all time symmetric. They don't have a built-in arrow. Let's put these fundamental laws on the stand. First up, Newton's classical mechanics. Imagine a film of the Earth orbiting the Sun. It's a graceful, predictable ellipse. Now, run that film backwards. You'd see the Earth moving along the exact same path, just in reverse. Nothing looks weird. The reversed motion is a perfectly valid solution to Newton's equations. Run a video of two billiard balls colliding in reverse, and it still looks perfectly fine. The physics works. So, classical mechanics? No preference for past or future. It's got a solid alibi. Next, Maxwell's theory of electromagnetism. These are the rules for light, electricity, and magnetism. They describe waves, like light waves, radiating outward from a source, like a light bulb. That sounds directional, right? But the equations themselves are perfectly time-symmetric. They also allow for waves that converge inward onto a source from all directions. We only ever see the outward kind in nature, but the fundamental law allows for both. Electromagnetism points the finger back at the source, not its own rules. Alibi holds up. How about the behemoth of modern physics, Einstein's general theory of relativity? Our best theory of gravity. Here, too, the core equations are time-symmetric. A star collapsing to form a black hole is a valid solution. But so is the time-reversed version. A white hole that violently spews matter out. We see black holes, but we don't see white holes. Again, the laws allow for both. The fact that we only see one of them must be due to the way our universe is set up, not the law itself. Finally, we turn to the strange world of quantum mechanics. For the most part, its main recipe, the Schrödinger equation, is also time-symmetric. Now, any good detective knows to look for the fine print, and there is a tiny asterisk here. There's one corner of the subatomic world, involving the weak nuclear force, where a tiny violation of this symmetry has been seen. But this effect is so incredibly subtle, it's like finding a single, out-of-place fingerprint at a massive crime scene. It's a clue, but it can't possibly be the reason my coffee mixes and never unmixes. The interrogation is complete. We've questioned all the fundamental laws of physics. And they all tell the same story: it wasn't me. Their alibis are ironclad. The rules that govern reality at its most basic level do not contain a direction for time. This leads to a stunning conclusion. The arrow of time isn't explained by how the universe works. It's explained by how the universe was. If the laws don't care about the starting line, then the only thing that matters is where the race began. Our detective story has to leave the present day and travel back 13.8 billion years. We have to investigate the scene of the ultimate crime, the Big Bang. The origin story. The cosmological arrow. Our investigation has taken a pivotal turn. The laws of physics are innocent. This leaves only one possibility. The arrow of time isn't a feature of the rules, but of the game board's initial setup. To find time's direction, we have to look to the origin of time itself. The Big Bang. This brings us to the cosmological arrow of time, which points in the direction of the universe's expansion. For about 13.8 billion years, the universe has been expanding. Galaxies are rushing away from each other. This expansion gives a clear direction to cosmic history. Forward is the direction where the universe gets bigger and colder. The link between this expansion and our old friend entropy is the critical clue. The second law says entropy has to increase. But for entropy to increase, it must have started low. If the universe had started in a state of maximum entropy total disorder, nothing could ever happen. It would be a static, heat death. The very fact that things do happen, that stars are burning and you are thinking, means our universe must have started in a state of absurdly, mind-bogglingly low entropy. This is the big reveal. The reason time has a direction is because the universe was born in a state of supreme order. Now, that might sound totally backwards. We think of the Big Bang as a chaotic, fiery explosion. How could that be ordered? The key is understanding what order means when gravity is running the show. In the first moments, the universe was incredibly hot and dense, but it was also astonishingly smooth. The matter and energy were spread out with almost perfect uniformity. And when gravity is the main force, that smoothness is the ultimate low entropy state. Think of it like a perfectly balanced, precarious tower. It's a highly specific arrangement. A much more disordered, high-entropy state for a gravitational system is one where matter has clumped together into things like black holes. The initial smoothness of the Big Bang was a state of immense potential, allowing gravity to slowly pull matter together to form stars, galaxies, and everything else we see. The early universe was like a perfectly wound-up clock. The Big Bang didn't just set the clock ticking. It wound it up to a state of near-perfect order, allowing the second law to drive its unwinding for the next 13.8 billion years. The two arrows, the expansion of the universe and the increase of entropy, are really one and the same, both pointing away from that singular moment of creation. We've found the source of the arrow. It was fired from the bow of the Big Bang. But in solving one mystery, we've stumbled upon an even bigger one. Because now we have to ask the ultimate question. Why? Why did the universe begin in this extraordinarily special state? The odds against it are staggering. If you just threw a universe together, it would be fantastically more likely to start as a messy, clumpy, high-entropy disaster. Our universe began in a configuration that is, by some calculations, as unlikely as 1 in 10 to the power of 10 to the power of 123. That number is so huge that if you tried to write it out, you'd need more zeros than there are atoms in the entire observable universe. This isn't just unlikely, it's a statistical miracle that demands an explanation. Answering this takes us to the absolute frontier of physics, to a puzzle with a deceptively simple name: the past hypothesis. The Y-files. The past hypothesis. Our investigation has led us to the core of the mystery. Time has an arrow because the Big Bang was an incredibly ordered, low-entropy event. But that just pushes the question back. Why did it start that way? This puzzle, why was the early universe so ordered, is so central to physics that it has its own name: the past hypothesis. But naming it doesn't explain it. It just highlights that this is a brute fact we have to assume to make everything else work. It's like finding a perfectly working Swiss watch in the desert. The real mystery is how it got there. So, how do we explain it? Here, we leave established facts behind and enter the world of speculative, mind-bending theories. Our detective notebook is about to get weird. One of the coolest ideas comes from physicist Sean Carroll and his collaborator Jennifer Chen. They suggest our Big Bang wasn't the beginning. Instead, picture an eternal, static, multiverse that's basically dead in a state of maximum entropy. But, within this dead sea, random quantum fluctuations happen. Most of them fizzle out. But once in a super astronomically long time, a fluctuation could be just right to create a little low entropy CETA, baby universe, that then explodes outward in its own Big Bang. Here's the beautiful part. From that low entropy birth, time's arrow would fly forwards into an expanding universe like ours, where entropy increases. But it would also fly backwards into another universe that, from its own point of view, is also expanding and increasing in entropy. Our Big Bang isn't the origin, but just a symmetric midpoint between two universes flowing in opposite directions of time. In this picture, our universe's special beginning isn't so special after all, it's just a rare, random event in a much larger system. Another set of theories tries to solve the puzzle by getting rid of the beginning altogether. This is the no boundary proposal from Stephen Hawking and James Hartle. They applied quantum mechanics to the whole universe at its earliest moment. They proposed a model where the universe doesn't begin from a single point. Instead, as you go back in time, the difference between time and space dissolves. Hawking put it this way. Think of the South Pole. If you're standing right on it, you can't go 1 mile south. The direction doesn't exist anymore. In their model, asking what came before the Big Bang is just as meaningless because time as we know it didn't exist. The universe just is, finite but without a boundary or an edge. This elegant idea could explain the smooth, ordered initial state as a natural consequence. What all these wild ideas have in common is that they're trying to answer maybe the biggest question in all of cosmology. We've traced the arrow of time back to the Big Bang, and the Big Bang back to the puzzle of the past hypothesis. We don't have the final answer, but the investigation itself reveals something profound about us. Connecting the dots, the arrows of a human life. Okay, so the final act of our story is to bring it all back home. We've gone to the edge of the cosmos, but what does any of this have to do with our own personal experience of time? As it turns out, everything. All the arrows of time we experience are just shadows cast by that one great arrow of entropy. Let's start with the most personal one. The psychological arrow. Why do we remember the past, but not the future? Think about it. What even is a memory? It's not some floaty, abstract idea. It's a physical thing, a pattern of neurons connected in your brain. To form a memory, your brain has to do work. Neurons fire, chemicals are released, connections are made. Every one of these biological steps is a physical process. And like all physical processes, it's inefficient. It burns energy and releases waste heat, increasing the total entropy of the universe. Essentially, making a memory means creating a tiny pocket of order, the memory trace. But you pay for it by creating way more disorder, waste heat, in the universe as a whole. You can only make a record of something that's already happened. We remember the past because our brains are swimming downstream in the river of increasing entropy. We can't remember the future because the universe hasn't gotten to those messier states yet. Our very sense of time's flow is a neurological consequence of this process. This leads right to the causal arrow. Why do causes always come before effects? Why does flipping a switch turn on a light, but you can't turn on a light to make yourself flip a switch in the past? Again, it's all about probability and entropy. We can influence the future because we can easily create ordered conditions, like flipping a switch, whose consequences will be more disordered, light and heat spreading out. We can't influence the past because that would mean our actions now would force the universe into a less probable, more ordered state in the past. That's like shouting at shattered glass to make it reassemble. Causality flows in the direction of increasing entropy. Finally, there's the radiative arrow. Why do ripples in a pond or light from a star always expand outwards from their source? The laws of physics don't forbid the reverse waves converging perfectly onto a point. But again, it's just statistically impossible. For random energy from all over the universe to perfectly time its arrival at one point to create a star is just not going to happen. All the arrows point in the same direction. From the expansion of the cosmos to the firing of a single neuron in your brain, they all trace their origin back to one fundamental fact. The universe began in a state of extraordinary order, and it's been getting messier ever since. This journey into time shows how deeply connected we are to the cosmos. The flow of time in your own mind is a direct result of the state of the universe 13.8 billion years ago. The biggest mysteries in physics aren't just out there, they define the fabric of our experience. If this is the kind of stuff that gets your brain buzzing, the huge questions connecting us to the cosmos, then you're in the right place. Seriously, consider subscribing and joining our crew of cosmic detectives. We're on a mission to unravel the biggest ideas in the universe, one mystery at a time. So, I've got a question for you. We just tackled the arrow of time, but what other giant cosmic mysteries keep you up at night? What should we investigate next? Let me know in the comments below. So, where does our cosmic detective story end? We set out to solve the mystery of why time has a direction. We started with a shattered teacup that never reassembles. We discovered that while the fundamental laws would allow it, the brute force of probability, the second law of thermodynamics, makes it a practical impossibility. We learned that this relentless march towards disorder, entropy, is what gives time its arrow. But this only works because the universe was handed an incredibly ordered, low-entropy starting point at the Big Bang. And there, at the dawn of time, we were left with the ultimate cold case. The past hypothesis. Why did the universe begin that way? A rare fluctuation in a multiverse? The natural state of a universe with no beginning? Or a clue to physics we can't yet imagine? We don't have the final answer. The case remains open. But maybe what we found along the way is even more profound. The arrow of time isn't some cosmic tyrant. It's the universe's storyteller. It's the narrative thread connecting the fiery birth of the cosmos to stars, planets, and us. It's the reason we can learn from the past and make choices that shape the future. We are all living in the unfolding consequences of that one special, low-entropy moment. We are all children of the arrow of time, surfing a great cosmic wave of increasing entropy that began 13.8 billion years ago. And the real mystery isn't that a broken cup can't unbreak. The real mystery is that, thanks to that special moment long ago, our universe has a story to tell it all.